let's get into making some games with Unreal Engine. First, we're going to go through the very basics and just explaining what all your options are with Unreal. So before we even open the engine, having the Epic Games launcher, you will find you have a marketplace tab. On this marketplace, there are hundreds and thousands of assets that you can purchase and use in your own game. Some are animations, some are models, some are particle systems, some are pre-made systems that you can integrate into your own coding, and they range from being very, very small to being absolutely huge. What you're probably more so interested in though is that there's also a free tab where you can get a lot of assets for free use. As you can see, all of the assets that you're seeing here entirely free. This includes a lot of projects that you can use for learning. There's this tab called Quickel Megascans, which are 3D scans of real objects in very, very high detail that you can use. There is the permanently free collection, which is just a bunch of assets that are free to download and use forever. All of the other ones we've had before also are free forever, but there's one little other category, which is free for the month. Every month, this will refresh with 4, 5, or 6 assets, usually adding up to a value of about $300. And if you buy the assets for $0, because as you can see, they're priced all the way to free, they are yours to keep forever. So every month, you should be checking in on the free for the month collection and just get all of them. Because there's literally no downside to having these all. And that will increase your library of usable assets, which will then, for a lot of different projects, be very, very useful to be able to use. And of course, once you get comfortable and good enough with Unreal Engine, you can start making your own assets and selling them on here to actually make some money off of using Unreal Engine. Which gets us into the library tab. Up top here, we have our engine versions. As you can see, I'm using engine 5.1.1, but I've also got 5.2.0 installed. For the series, I'm going to be using 5.1.1. If you're using 5.0 or 5.2 or eventually maybe a 5.3 or 5.4, largely things should still apply the same. At least until there is an eventual Unreal Engine 6, at which point I might make a new series as well. Under that, you see a list of all the projects that you have made and that you're working on. And then at the very bottom, you've got your vault, which is all of the marketplace assets that you own, which also has a search function. So let's say that I want to get my Unreal camera system, which is a marketplace asset that I have made. I simply type in Rail, and then we get the dynamic Unreal's gameplay camera, as well as surface trails, because that has the word rail in it as well, and a Victorian train, station, and rails. So it's got a pretty decent search engine in there as well. With all that out of the way though, let's launch the engine and make our first project that we're going to be working on. And here we have a selection of templates. You've got a blank template, which I don't think I have ever used this one, but if you're working on a game that doesn't fit within any of these templates, that's the one you would go with, but more often than not, you'll probably end up using one of these. Because if you're making a shooter game, or a walking simulator even, or whatever, a first-person template already exists for you. And that includes a first-person movement, walking around, looking around with your mouse, that kind of stuff. Third person, very similarly, already has movement and a default character set up for you to be using. The top-down is a point-and-click system, so you click somewhere on the screen and the character will move into that direction. And then I've got vehicle, which is things like racing games and stuff like that. I've never really used that too much, so I can't really tell you what that is like. And then we've got a handheld AR and a VR template as well, which, if we're ever going to get into that, that's going to be a series in and of itself. In this series, we're going to be making a simple 3D platforming game. So we're going to start with the third-person templates, where you can then choose whether you want to use Blueprint, which is what we're going to be doing for this series, or C++, which is a little bit more advanced, and I plan on making a more intermediate course aimed at specifically C++ in the future. But for now, we're going to stick with Blueprint. The target platform can be desktop or mobile. We're going to stick with desktop. The quality presets. For the most part, we're going to stick with maximum here. If you're releasing on a bunch of different platforms, maybe you want to be able to use scalable, but for the most part, it doesn't really matter that much. Starter content, that will include a bunch of simple materials and objects that you can use, which are always nice to have. And then ray tracing, we're going to keep off for the time being. And then down here, we can give our project a name. So let's call this Unreal Basics Tutorials. Project name can only be 20 characters or shorter, so we're gonna stick with Unreal Basics Tutorial. And then the project's location, you can put it wherever you want. And then we can create our project. And this is the screen that you will be greeted with when you open up that project. The most important button we're gonna go over first here, and that is this button up here. This will allow you to run the game and test everything out. And as you can see, it's running rather slowly, and that is because it's still building a lot of the materials and shaders and stuff like that in the background while the project has already started up. So give that a moment and it should run a little bit smoother. Then over here on the right hand side, we have the outliner, which is a list of all of the actors. We'll get into what an actor is, but think of it as all the objects that exist inside of this level. So if we just click on this one, the quarter cylinder 11, you can see it highlights it in the viewport, which is what this window of the actual game world is called. That's the viewport. Holding the right mouse button will allow you to look around in the viewport, and then you can fly around in the direction that you're looking with W, A, S, and D. It's very much like controls would be in an actual game, which is very, very nice. So we can go closer to this object and we can see, okay, so that's the object we just selected. If we can't see whatever object we just selected because it's too far away, you can also press the F key and the engine will just get you over to that selected object. Now, you will see this little gizmo over here, these arrows, and that will allow you to move around the selected actor. Very simply like this. You'll also see that in between the arrows, we've got these little corner pieces. If you drag it around by that, it will move it into both of these axes without moving it in the remaining one. If you grab it at the exact center, you can freely move it in all three axes, which generally speaking is not something you really want to do because it's kind of hard to judge distance and location in 3 dimensions at the same time. Coming up here, we can also change that gizmo into a gizmo that allows us to rotate the objects, and it will rotate around the point where the gizmo is, which is the pivot point or the origin point of the object, which can be set in an actor in a number of different ways, or if you're just importing a mesh into your scene, that will have to be set in your modeling tool of choice, something like Blender or Maya or whatever you might be using. So we can use this to rotate this thing around as well in much the same way. As you can see, it's rotating around this bottom left corner. The next one over allows you to scale the objects, again, in any of the axes that you want, in a combination of the axes, or in all three at once. For scaling, using this bottom left one, which selects all three at once, generally is a much more useful one than it was for things like moving this around. And you might have been able to see that these three things have shortcuts. So movement will be enabled when you press W. Then when you press E, it will change to rotation. And when you press R, it will change to scale, which is a little bit confusing because you would assume that rotation is R, but it's not, because these 4 buttons here correspond to the exact same layout on your keyboard, that being Q for the cursor pointer, which I don't often use, to be honest. Then W for movement, E for rotation, and R for scale. And while we're going through all these icons, I might as well cover the rest of them. The next one is whether or not the gizmo applies movement and scale and rotation in world space or in local space. And this might be a little bit tricky to wrap your head around. But as you can see, we can rotate this thing like 50 degrees in some direction, right? And then if we go back to movement, we still move it along the same axis relative to where it is in the world. Then if we change this thing to local position, look at what happens to the gizmo. It lines up with the rotation that we applied to the object. So now it's moving in the world along its local axis, meaning that its rotation now does affect how we're moving things around, which can be very useful, because if we rotate something around and then we just need to nudge it a little bit more in like its own forward direction, this is very useful. Most of the time we do tend to stick with using the world space gizmos though. Then we have surface snapping, which is something that I personally really never use too much, because the next couple of options are snapping things to a grid. So you can see if we go outside here, we have this grid pattern, right? And each one of these little squares over here is what we call 1 unit of distance. And you might have seen before when I was moving things around that things move in a pretty snappy way. And that's because right now it's snapping when it's moved around to every 10 units. So I can set that to every 1 unit. And then you'll see that the movement is a lot more precise. But it's also harder to line things up properly so that they don't clip through each other. I can also set the clipping to something much higher, like 500 units, in which case I can only move them around with every 500 units, which is very useful if your objects are significantly larger. Just pressing this little button over here next to the number will just disable snapping entirely and allow you to move things freely, even more precise than a unit. And the same thing goes for rotation. Usually I like to have my rotation set at a 45-degree angle for snapping. That way I can move it around to 45 degrees and 90 degrees and every 45-degree step around. Scaling, I don't think I need to explain anymore. We can do the same thing for. You will see that it snaps a little bit with the scaling. We can set the scale snap to something like 10 to really show that off. And now you'll see, oh, it only scales up massively right away, which is not necessarily something that we want. And then we've got the camera speed here, which is the speed that the camera moves around in the viewport. If you're working on a very small scale scene, you're gonna want to have this set to a lower number. But if you are working on a massive like cityscape or something like that, setting that to a higher number can be very beneficial. Then we have the very last button over here, which maximizes or restores the viewport. It says it's not really a good explanation of what it does, because what it does is it splits up your viewport into 4 pieces. One that is like the active camera that you're working with, and then we've got a couple of different perspectives as well. So let's focus on this object here, on all the viewports, and you now can see that this is the view from the back, which usually I actually prefer looking at things from the front because it makes a little bit more sense. And then we've got the view from the right, which is from this direction going into there. This can be some useful perspectives, but the most useful one generally is the top perspective, because it allows you to look at things from the top view, especially for lining things up like this. That ends up being very, very useful. And then pressing this button again will maximize it back to being just 1 viewport. If you don't want to split your viewport up into 4, you can do the same thing over here. Going, instead of perspective, we have all the different options here as well. So we can just look at the top from here, find the thing that we're working with, and now we have a full viewport just from the top. You'll also note that we suddenly don't see the textures anymore when we go into one of these, and that's because the thing that's right next to it changes to wireframe. We can set this back to lit, and we just see the level in its entirety. There's a couple of different modes that are useful here as well, like unlit. This is just the basic textures. Let's go back to perspective real quick for that. Without any lighting applied, which can also be very useful if you're working on a very complex scene with a lot of lighting in it that hasn't been baked yet. We'll get into that at some point later. And your computer is having trouble, you can just set it to unlit if you're just moving around some objects and you don't need to worry about what the lighting looks like. And in much the same way, we also have one that only shows the lighting, so everything just becomes blank textures so that you can really look at what does the light actually do. We've got some collision related ones, but usually we stick with lit, unlit, and sometimes wireframe. Those are the three most useful ones. And in much the same way, we have a bunch of viewport options here as well. I'm not going to go into those right now, just take a look through them if you're curious. Like, I can enable the collision, and that will now show the collision around all of these meshes, which is a not unimportant thing to note. For instance, these cylinders over here, they are very round, and there's no real good reason that the collision should be that smooth, because that's only going to take up more computing power. So the collisions for them are actually a lot more rough around the edges, because that's, generally speaking, good enough. And that's the kind of thing that you can see when you enable the show collisions. And in much the same way, all of these other things can be very useful to just take a quick look at. Now, that's a lot of information. I don't expect you to retain all of that right off the bat. I'm just showing you everything so that when it does become relevant, you already know that it exists, and we can go into it a little deeper again at some point in the future. There's two last things that I want to walk you through before we end over this first introductory part to the series, and then next time we're actually going to get into a little bit more detail what actors are and how they work and how you actually build up your games. Before that though, if we have something selected in our outliner over here, which again, remember, these things are called actors, we'll also see that in the details panel over here, we get the, what do you know, details about whatever actor we have selected. So if we select the static mesh cube over here, we can see that the static mesh cube here has a static mesh component. We'll get into components a little bit more in the next part as well. And then there's a bunch of information here to it as well, because every actor needs to have a transform, which is the location and rotation and scale, where it is at in the world, what direction it's facing and how big it is. It's got a mobility mode, which is either static, which is used for things that, generally speaking, aren't supposed to move. It's just an optimization thing for lighting. If it doesn't need to move, you can just apply lighting to it once and then don't need to update it every frame, which saves a lot of computing power. On the other side, we have movable things, which are things that can move around in the game, meaning that if they either emit light or need to be able to have light cast onto them, which pretty much everything needs to be able to have light cast onto it because that's how we see things, that's what you set movable for. Stationary is a kind of in-between. It's things that, as the engine calls it, can be changed but not moved, which is a very cryptic way of explaining it, and it's kind of hard to explain what stationary is actually good for. In a general sense, you can think of it as a slightly better looking but also slightly less optimized version of static. Then this specific actor has a static mesh, which also comes with a material. It has some physics options, collision options, and so on and so forth. We don't need to go through everything that's present here because it's quite a lot. But just know that when I select a different actor in our outliner, which has different properties, such as the directional light, we see that it has different things in the detail panel here. We have the transform because, again, everything needs to have a place inside of the world. But then we have some options for light, such as intensity. If we increase this, we can see the world gets a fair bit lighter. And the light color, which we can make like purple, and everything becomes purple. Because the directional light, which we'll get a little bit more into towards the later parts of this series, where I go into lighting and stuff like that. A directional light is a light that casts from the same direction throughout the entire level. So it's kind of like a sun. And finally, the very last thing that we're going to go into right now is if we come down here to the bottom left corner of the screen, we can see our content drawer. And this is actually where all of our assets live. This is where we can organize them, just like a folder on your Windows or your Mac or your Linux device. I don't even know if you can use Unreal on a Linux device. You probably can. And this template comes with a few different folders pre-set up for us. So we have characters and mannequins, and it's got all the animations in it and the animation blueprints and 2 different mannequins and stuff like that. If we go into the third person folder, we can see a blueprint, and we have the BP third person character. We can drag that into the scene, and we can see it's now in our scene. And this is what our player character is. Now, this won't work as our player character because we have a player start right over here. That's a little bit too needlessly complex to really get into right now today as to why we want to use a start player instead of just putting our player character into the world like this. But this is how we just take assets that we have made or imported and put them into our actual levels, which is a rather important step in making a game, obviously. Next time we're going to go into a little bit more detail about actors, what they are, how they're structured, and how to use them. Welcome back to the basic for Unreal. The last time we had a big info dump about a bunch of different things about the interface for Unreal. Today we're going to go into some actual technical stuff, that being what actors are, how they work, and how you can make your own. So we've got a actor blueprint over here that's been pre-made by the template that we're using, and this is a character. So we can just drag that in, and now it exists within our world. And as you can see, my performance is kind of bad. There we go, that's much better. It exists in our world now. So that's how we put things into the world. But how exactly do we make our own? Well, let's go back to our content folder here, up top. And we can just right click in our content drawer. Also, if you're wondering how I'm pulling up the content drawer like this without clicking on it, if you press Ctrl and space, it just automatically pulls it up no matter where you are in the engine. We can right click in our content drawer, and there we can add a bunch of different kinds of assets. And we'll eventually go over the most important ones of these, but for now a blueprint class is what we want to make. And when we make a blueprint class, you can see we have a parent class that we need to pick. And this is where things get a little bit complicated, so stick with me. Because up top here we've got the actor, the pawn, and the character. These 3 form a hierarchy. And what I mean with that is that the actor, every object that you put inside your world is going to be an actor. Meaning that they have all of the functionality that is pre-existing within the actor class, as it's called. That is things like having positional data, like the transform we discussed before. It has the capability to check and deal with collision and physics if you wanted to. It has the capability of holding components, which you can see on the bottom here, an actor component or a scene component, which we'll get into in a moment. And it has some other things like a event called begin play, which will execute code as soon as the actor is put into the world. An event called tick, which will run every frame that the actor exists in the world. That's all coming from the base class named actor. When we click on this, we get a new blueprint class based on that. So let's call this test actor. And generally it's good to prefix this by putting BP underscore in front of it. That way at a glance you can see, oh, this is a blueprint. And if we open it up, we now get a window here which we can dock up there. And we have our basic actor here. Now, it's important to note that, and this is where things get a little confusing, specifically that this blueprint itself is not really just an actor anymore. This is now a BP underscore test actor, meaning that it has all the functionality that the actor class itself has, but we can build on top of that. We can give it extra data. We can give it extra scripts. and that builds on top of what actor already does. If we now go back and make another blueprint class, that is exactly what a pawn does. A pawn is a pre-existing extension of an actor, and this relationship is what we call a parent-child relationship. So actor is the parent to the pawn, meaning that a pawn takes all the functionality that the actor has and then adds its own functionality on top of that. And here you can see what that is. A pawn is an actor that can be possessed and receive inputs from a controller. That can be either the player controller or a AI controller. Then we have the character, which is a child of the pawn. So the pawn is the parent to the character, which by inheritance also means that the actor is a parent. You could call it a grandparent if you wanted to, I suppose, to the character. And the character is simply a pawn that includes the ability to walk around, specifically meant for humanoid characters. And if we make a pawn real quick and we call that BP test pawn, we will see that if we compare the right hand side here on the details panel to the test actor, we see that there's a couple of new different things, and that is use the controller rotation, use the controller yaw and roll, and can affect next generation, auto possess player, auto possess AI, and AI controller class. Then we've got some input stuff here as well. That is what the pawn adds on top of what the actor already was capable of. Now let's also make a character, just to show you that that extends that even more. BP tests character. I also know that these all have unique icons to them. The moment you start adding your own meshes to these, that's what will get displayed instead. But it's nice to have a visual reference of what kind of actors we're working with, whether it be a normal actor, a pawn, or a character. And when we open up the character, you'll definitely see that this has quite a bit more going for it, because this now has a capsule component, which is used for collision. It has an arrow component, which usually isn't really used for any specific functionality purposes, but it's nice to be able to have a reference to what the actual forward-facing direction of your character will be. And it already has a mesh put into it as well. So we can select a skeletal mesh asset, which is something like this, and we can pull that down and rotate it, and maybe even scale it down ever so slightly. I've got the scaling still set to being way too much. So scale it down ever so slightly. And that is basically how we set up a character. Then you see this little line over here before we go to the character movement component. And this is the component that has been added that will allow this character to move around in a pre-made way for us. And it's a really powerful tool to be able to use, because this allows you to set the gravity scale on an individual basis per actor, the maximum acceleration, a lot of things for walking, settings for jumping and falling. It's even got pre-built swimming and flying controls in it as well. And now that I'm showing off this component, I think it's a good time to start talking about some other components. So let's close out the character and the pawn, because I'm just going to show this in the normal actor. Because the normal actor by itself doesn't really do much. The only thing a actor does without any extension to it is existing. It doesn't have any collision. It just has the capability to detect and calculate collision. It doesn't have any other sort of functionality, because we're going to need to add that through adding either scripts through the event graph, which we'll get into in the next part, or components. And the components together is what is your actor in total. So let's try to add a component here. And you can see there's a bunch of different options that we can add in here. But for the time being, let's go for a static mesh. A static mesh is a mesh, so a 3D object, that's not been animated. And when we add that, we can see it gets added into the hierarchy here. And we can call it something, let's just call it mesh. Having that selected on the right hand side in the details panel, we can see the static mesh here, which will allow us to pick one of the static meshes that this project holds, which is quite a few of them. So let's go for, I don't know, the cone. That seems kind of fun. And we can move that around and we can scale that up a little bit if we wanted to. And we can save that and compile. If we then go back into our test map here, we can see that our blueprint class now has an image of the thing that we put in it. And we can drag that in and we have the cone. The cone still doesn't do anything, but we can now see we added the components, we gave it a value for the static mesh, and now we can put that into our world. It's worth noting that you can put static meshes directly into the world as well, but then they won't have any functionality or any sub-components. And that's the brilliant thing that we can do here, because we can add another component. Let's say we want to add a sphere component on top of this, right? And as you can see, it's in a sub menu almost. We can collapse this of the mesh, meaning that this is now a child of the mesh. So just as the classes themselves have child-parent relationships, so do components in the hierarchy. But it means something slightly differently in practice, because what this does is when I move this mesh, it moves all of its children around with it. And if I rotate this, the children maintain the same relative position to its parents, which can be a very useful thing to be able to do. And the most wonderful thing now is, if we put this into the world, we can see it immediately has the new component that we added to it as well. So let's add another component. Let's add a cube. Why not? And that cube is going to not be a child, right? Just to show you the difference here. So if we just drag this up to the default scene root, we can say attach, or we could have made it the new root as well, which is the pivot point of this actor. And we can move this around now, and we'll see, moving this set of meshes around, the cube doesn't move with it. The best part though is we now added a cube, and that immediately is visible in the actor that we already previously placed in the world, which is fantastic. That then gets us into the two different kinds of components that we have, because you might recall when we made this blueprint class here, we could see a player controller and a game mode base as well. We're not going to get into that for the time being, because that makes things overly complicated. But we had an actor component and a scene component. And let's just read what it says. An actor component is a reusable component that can be added to any actor. Well, it's not very informative, is it? But a scene component is a component that has a scene transform and can be attached to other scene components. So everything we see here, this cube, this mesh, and this sphere, these are all scene components because they have a physical location inside the world. A actor component, on the other hand, doesn't have a physical location. It's just some bit of data or some bit of script that's attached to an actor that doesn't need any place in the world. So it doesn't need to have a collision, it doesn't need to have a location, it's just only information. And one of the scene components that is very nice and useful to be able to use is one called the rotating movement. And you will note that we can't attach this rotating movement to any of our scene components because it itself isn't a scene component. If we select a cube, we see it has a transform. If we select a rotating movement, it does not, because it doesn't exist in the world. All it does is tell these other components that it needs to do something. That being, it's going to make the default scene root rotate. So if we now run the game, we'll be able to see that this thing rotates because it has a rotator component. So if you have a character that needs to have something like a stats component, right? That's something that is very useful for, where it would hold the information about its max HP and its current HP and its attack value and its defense value, maybe a magic value, all those different kind of things. Those you could put on a actor component because it's just information that doesn't concern itself with any physical location inside the world. Something like an inventory as well would be an actor component. And with the mix of the scene components, which exist in the world itself, and the more abstract actor components, you can mix and match to create whatever actors you want. And that is the basics of how actors work in Unreal Engine. So we've got actors, which is literally any object in your game is a child of the actor class. Then anything that can move on its own volition, that being AI or a player, is going to be a pawn. Because a pawn is an actor which just has the ability to get input controls and do something with them. If it needs to be a semi-humanoid, at least, character that needs to be able to walk around and things like that, you're going to want to make a character, which is a specialized version of a pawn. So again, we've got an actor, which has a child, which is the pawn, which is a child, that is the character, and there you then create children of your own. And that you can infinitely extend. So let's say we make our test character here. This test character could very well have some functionality that is shared by both the player and the enemy AI. So what we could do is we could add that functionality to this, and then when we right click this, we can create child blueprint class, in which case this would be test character player. And if we make another child blueprint class of that, we could have a test character enemy. And now anything we put into this test character will also be present in both of these children. And then we only have to make the thing that makes these different inside of the children, rather than having to copy over all the functionality from the test character itself. This again is a lot of very dense information about how the engine and the workflow is structured. And just like in the last part, I definitely do not expect you to internalize all of this information right away. So if you're still a little bit confused as to how this actually works, don't worry, I fully expect you to be. As we go along and we actually put all of this information into practice, you can always come back to this video to remind yourself of how exactly things work, and over time things will click and sink in, and you will start to understand what all of this mumbo jumbo that I've just spouted at you for the past however many minutes actually means. Next time we're going to go into one of our own actors, and we're going to open this events graph in which we'll be using these events to make a little simple script to get us into actually programming our game. Finally, we're going to be able to actually do some programming in Blueprint today. We've spent a lot of time in the previous parts, if you've seen those, explaining the engine and how everything works and the systems that make your workflow efficient. Today we're actually going to implement some actual coding, which is going to be very, very exciting. In this series we're trying to make a 3D platforming game slash kind of an obstacle course type of game, which is a very good, simple example that allows us to show off a lot of different things. So what I'm going to do for the time being is in the viewport here, I'm just going to delete a lot of these objects over here because we're not actually going to be using most of this. I will, however, keep these around because these will be useful in the next video that we will be doing, which will be talking about collision and physics, because these blue things over here are physics objects. And this leaves us with a nice and empty testing ground for our new actors. So let's make that new actor. First and foremost, we're going to go in here and I'm going to delete the actors that I have already created to show off the actor system. And we'll make a new actor, which is going to be a normal actor, which we'll call BP Sweeper. Opening that up, we are going to do something that we've already done in the previous part. We're going to add a static mesh, or in this case, actually, we can just get away with a simple cube. And then coming over into the transform, make sure that the scale is not locked, because if it is, it will always scale proportional into all directions. We don't want that. What we want is we want to scale this thing in either the X direction or the Y direction. It doesn't really matter which direction we go in. And let's scale this to like 10 times the width. And then in the opposite direction, we're going to scale this to like 0.3. So that's a little bit thinner. And we'll scale it up to being twice as tall. Now we have a nice little wall. And if we add a rotating movement component to this, We can set its rotation rate around the z-axis, which is the up and down axis, to something a little lower than 180, something like 15. And now, when we put that into the world and we play the game, we can see we have this thing sweeping around. And it's a little bit buggy because of the whole collision situation, which we'll get into a little bit later. And for all that, we didn't need to do any programming. It's literally just adding a couple of components and that's it. So let's do something a tiny bit more complicated before we go ahead and fix the issues with this thing, because that's going to also need a little bit of blueprint programming. For this, we'll make another blueprint class, which is going to be of type actor, and we'll call this BP pusher, where we'll add another cube, and we can set this to, and you see we have it still on not being locked, but this time we actually want a cube. So let's lock it and then set it to being about 10 times the size. Now, if we open up the event graph, we can see we have a onBegin overlap event. We're not going to be using that for the time being. A event begin play, which we're going to be using in a moment here, and an event tick. I mentioned these a little bit before in a different part, but if you haven't seen that one, let me go over it real quick again. Event begin play is a event that will execute a certain script or a piece of your code when the game starts, or if this object is spawned in after the fact during runtime, this will just run the moment the actor gets placed or spawned into the world. Event tick will run whatever code is hooked up to it every frame that the game runs. So if the game runs at only 10 frames per second because it's horribly optimized or it's on a bad PC or whatever, this is going to run 10 times in a second. However, if your game runs buttery smooth at like 120 frames per second, this is going to run 120 times in that second. So this is a very useful and powerful event to use, but also one that you need to pay attention to, because if you're like adding a certain score amount to your character every event tick, if you just add one, it's going to be different depending on your frame rate. This delta second pin can help with that, but we'll get to that in a little moment. Next up, we have on the left hand side here the variables. This is the cornerstone of programming, a very fundamental basic thing. If you don't know what variables are, very easily explained, they are containers for information. I'm sure most of you are familiar with basic algebra. Say instead of calculating something like 2 plus 4 equals 6, we say x plus 4 equals 6. Now we can use this same formula if we want to add anything to 4. So we can just say x is equal to 2. So now we are back at 2 plus 4 equals 6. But if we want to add 10 instead, we simply say x is equal to 10, and now suddenly the same formula without any other interference on our part says 10 plus 4 equals 14. And you can definitely see in programming why that would be useful, because this allows us to build systems that don't have any actual concrete information, but allow us to feed in the information of any specific situation that we might be in, which makes for a very flexible creation of whatever system we want. So if we add a variable over here, we'll see it creates a new var. And it has a type. And this is very important because I said a variable is a container for information, but the variable needs to know what type of information we're going to store inside of it. So by default, it's making a Boolean variable, also known as a bool. And this can only store a binary state. So what does that mean? That means it can only store a 0 or a 1. Or in more easy to understand terms, it can store a true or false. So if we compile this right now, we can see we can set a default value to it, and it's a checkbox because it can either be false or true. There's nothing else to put in there. So the engine gives us a checkbox to do that with. And you'll also see that we can change the variable type either on the left-hand side here or on the details panel on the right-hand side. We can also make it a byte, which frankly, not that often used. So I'm not going to go into it right now. We have an integer and integer 64. We'll stick with normal integers for now. Integers are, as you would expect, just integers, which are whole numbers. So that's 1, 2, 3, 4, 5, but not something like a 1.5, right? 1.5 is a value in between 1 and 2 that we cannot store in an integer. So let's try that. 1.5, it defaults back to 1, because anything after a decimal place, you can't store that in an integer. An integer can store a value up to billions in the positive or negative. It's not unlimited though. There is a limit to how large the value in your integer can be. It's not an issue that you're likely going to run into, because again, the range goes from, I believe, something like -4 billion something to +4 billion something. But should you need to have a number that is significantly larger than that, that's where the integer 64 comes in. This allows you to store much higher value numbers. It also has a limit, but the chances of you ever reaching that limit are slim to none. Next up, we have a float, which is a floating point number. This is what we use for decimal places. So this, you can see, now has a comma in it. So we can say something like 12.753, and we can put that value with decimal places into this float. Then we've got names, strings, and text. These are all very similar. These store characters, so text. For any practical purposes, these are pretty interchangeable, because if you hook them up to a field of one of the other types, the engine will just put in a conversion node automatically in between. So if we go make a string, we can type in this is a test, and you can see it takes in a text. Then we've got a vector, a rotator, and a transform. If we go into a vector and compile that, you will see that this is a much more complicated type of variable already. Because this is not just a float, because we can still put in decimal places, but it's actually got 3 fields here: a x, a y, and a z. And this is where we get into, these variables are called structures, which is more or less just a custom variable that the engine provides you with, or that you could make yourself if you wanted to. And the most basic of that is just the vector, which is a variable that just holds 3 float values and some extra functions and events that you can use to do things with. So if we have a vector, I'll just drag this in. We'll get into the whole event graph in a moment. I can get the vector length, for instance, which is a function that corresponds to the vector type variable or struct. And this puts out a float of simply x plus y plus z. Then we have a rotator, which is very similar to a vector because it also holds 3 different values here. It's just got some different functions on it compared to what a vector has. And rotators, as you might imagine, are usually used to store the rotation of an actor or a component in them. You could store that information largely in a vector as well, but a rotator is designed to hold that information. And then lastly, we have the transform, which if we open that up, should look very familiar. It's got a vector in it because the location is just a vector. Then we've got the rotation, which is a rotator. And we've got the scale, which, as far as I am aware, is another vector. All put together in one type of variable, so you don't have to make a vector for your location and then a rotator for your rotation. If you want to influence those and store those, you can just put them all together in a transform. Those are the most basic versions of a lot of the variables that you're going to be using. Then there's a bunch of different other types as well. We've got enums, which we're not going to get into right now. We've got object types. So these are all of the different objects that exist, which means that we can make a variable, for instance, that is specifically of object type BP sweeper. That can then hold a reference to that object, and they will only be able to hold references to blueprints, to actors that are specifically of the type BP sweeper. If we put any other actor into this as a reference, it won't work and it will remain an empty variable. So any blueprint that you make is also then immediately going to turn into a potential variable type for you to use, which is a very important thing to realize. All that theoretical stuff out of the way, the reason I went over all of that is because we need a variable to store our starting location in. So we're going to make a vector variable here, and we'll call that our start position. Now, back in our event graph, we can drag in our start position variable here, and we can either get the value of it to read it if we need it in a formula or something, or we can set it to write a new value to it. So we can set it to something like 1, 2, 3. And the way we execute that set node is by connecting it up to a event. So at event begin play, this variable will now be set to a value of 1, 2, 3. But we don't actually want it to be set to a specific hard-coded value. We want it to be set to whatever location our actor is located at the start of the game. And for that, we can actually use a pre-existing node. We can right-click to add a new node, and then we can type in whatever we want. So we want to get our actor location. This will pull up a function node that will take in a target and then return a value. And that return value will be the location of the actor. You can put any other actor you want if you have a variable or a reference to it into here, and it will then return the value of the location of that other actor. If you don't put anything into it, you can see the default behavior here is self, meaning that this is going to just give us the location of the actor that this is on, which is our BP pusher. If we have 5 BP pusher actors in our scene, each one of those is going to have its own set of variables, and each one of those is going to run this function on its own instance. So I'll just show you that. Putting that in there, we definitely should make the cube a little bit smaller in a moment. If we have 2 of these, this one will run the function getActorLocation and get the location corresponding to this origin point. At the same time, this one will also run that function, but since this is a different actor altogether, it will then return the location of this point instead. So if we set this position now, we can connect it up like that, and now this variable is getting set to the result of whatever this function does whenever we begin play. And the way we can check that is to make this variable public. So if we set this variable to being public, we can then see it in our details panel that we've looked at before. So if we look at this here, we now see our starting position is set to 0, 0, 0 because begin play hasn't run yet. But now if we run the game and we look over at our pushes, this one has a starting position of 2154, 666 and 0. And then our other pusher over here has a different starting location because it's being put in a different location. Now, we're going to make 2 more variables, and one of those is also going to be a vector, and that will be called our movement direction, which will also make public. As a matter of fact, we're actually going to make the starting position not public anymore, because public variables usually are variables that we want to be able to influence on a per instance basis. So that means that we want to be able to just click on them and set them in the viewport here. So for instance, this one needs to move in the Y direction. So we set X to 0, Y to 1, and Z to 0. And this one we want to move in the X direction. We set this to 1 and 0, 0. Then we're also going to make a movement speed. And that one is going to be a float variable. When we multiply these 2 together, which is possible, you can multiply a vector with a float. What that will do is we'll just multiply the value of the float with each of the 3, the X, Y, and Z, stored in the vector. We will get a value of a certain direction multiplied by a certain speed that we can use to move these actors around. And that is what we will be doing in event tick. How do we do that? Well, we do that by using the set actor location. And as you can see, by default, the target is set to self. We'll hook it up into the event tick. And here we will use another one of these get actor location nodes because we want to get its current location and we want to add to that. So we can drag off this and then just simply plus. This gets us one of these math nodes, which allows us to add another vector to it. And the vector that we want to add to it is going to be our movement direction, which we can get, multiplied by our movement speed, which we can also get. We simply multiply those and then add that to our current location. And that we can set as our new location. So if we set our default movement speed to something like 10, we probably want to make that also a public variable because we want to likely influence that on a per instance basis. Now this thing will move in its given direction at its given speed every single frame. It's not exactly what we want, is it? Because we want this to be frame rate independent. That's where delta seconds comes in. Delta seconds is the value in seconds since the last frame ended rendering. So if you're running at 100 frames per second consistently, the delta seconds value will always be 1/100th of a second, so 0.01. If you're running at 50 frames per second, it will be 0.02 because there's been 0.02 seconds passed since the last frame. Since no game almost runs at a very consistent frame time, this delta seconds will probably change from frame to frame. And that is what allows us to make use of it, to make things frame rate independent. So if we move this over a little bit and we multiply our movement speed by those delta seconds, that simply creates a system where our movement is now the same speed independent of what frame rate the game runs at. So let's move these up so that they don't run into the walls because they're going to be only moving in one direction and not back for the time being. And we'll look at this one, right? So this one is going to be moving in the Y direction at a movement speed of probably 100 actually, because multiplying something by delta time makes it move a bunch slower. And as you can see, the one we set to the Y direction is moving in the Y direction, and the one we set to the X direction is moving in the X direction, with a very poor frame rate, which is mostly to do with the facts that I'm recording right now. It also has to do with our project settings, which I'm going to open up real quick, because I have a lumen global illumination set to true, and we don't want that for either illumination or reflection, because that's quite computing intensive. It does look very, very good, but it makes your game run like shit on lower end hardware. And while we're at it, I'm also going to disable the motion blur in here because I don't like the way it looks. And I'm also recording at the same time, so sometimes you will note that if you're working on the engine and you exit play mode, your objects are just gone. And that's because the engine's like, oh, wait a second, your computer actually sucks. Hold on a moment. I'm going to unload some of these objects. When we run the game again, they're going to be there. This is just a optimization thing to stop the engine from being so sluggish. So what you can do, you can select them and you can just pin them. That will always force them to be loaded if that's specifically something you're working on at the moment, which for these three objects, we are. Now, these blocks are moving and we're doing that through our own made code. So if that's working so far for you, give yourself a pat on the back because you've just made your first script. It's honestly that easy. But it's not very usable right now, right? Because we probably want these to be moving back and forward. And there's a bunch of ways we could be doing that. But for the sake of making things stay simple, we're going to be adding 2 more variables and doing a little bit of simple math. It's the most educational way to do it anyway. So we're going to be making a max move distance variable, and we're going to be making a is moving back, which that one will be a bool. You will also note that if you use this specific capitalization technique, where you capitalize the first letter of every new word, the engine will actually separate those into separate words in your details panel so that it's a little bit more readable because you can't have spaces in your variable names. Now, What we're going to do here is after we set our actor location, we're going to check if the new actor location is more than our max move distance away from the original location. There's a number of different ways of doing this, but the easiest way to do that would be getting our actor location and getting our starting position. You can just hold Control, by the way, and drag these into the event graph to immediately get a getting node for them. And if you do the same thing holding Alt, you immediately get a setting node for them. You'll be seeing me doing that a lot. So if you're wondering how that actually works, that's how you do it. And if you drag off a vector, we can use the distance function on it, which lets you plug in two vectors and returns a float. And that float will be the distance between those two vectors. So if our starting position is 0, 0, 0 and our actor location has become 0, 100, 0, the distance will be 100. Now that becomes exponentially more complicated when you're moving into more than one direction. And this function just calculates all that for you, which is very, very nice. And then we simply want to check that against our maximum move distance. Have we moved more? Is this distance more than we should be allowed to move? And there we can just simply check, is this greater than that? This would simply check top value being greater than the bottom value and output that in the form of a bool value, just like our Boolean variables have been so far. And that's the basics, the beginnings of building logic in Blueprint as well, which we will probably get into a little bit later at some point. If we hold down the B key for branch and click, we just immediately add a branching node, which takes in a bool, and when that bool is true, it will execute whatever we put into there, and when that bool is set to false, we execute whatever is set to there. We can put in a variable there if we want to, which we're going to do in a moment. But for now, we're going to put in the output of this little calculation that we've done here. Because if that distance is indeed greater than our maximum move distance, we want to start moving back. So we set our is moving back to being true. But that's going to be an issue, isn't it, actually? Because, well, that's a bit of an issue because we want to set it back to being false again when we get back to our starting position. So what we'll actually do is we'll drag in a reference to our current value for is moving back, and we'll simply type in not. This will just take in a bool and output the opposite value of whatever it is. So all this is doing is saying take our is moving back, invert it, and set that as its new value. And if this is false, we won't be doing anything. Now, in order to make the moving back itself work, we're going to put in a branch node here as well. Because if we are moving back, we want to move into this direction, but in the negative direction of that. So as long as this is false, we are not moving back, we're moving forward, all of this still applies. But if we are moving back, we want to create a second set actor location. We want to do all of this, but we want to multiply this by -1. Issue being is that this is 3 values and we just want to multiply it by 1 value. So we can right click this bottom pin, convert the pin to a float, either single or double precision, it doesn't really matter. And then the bottom pin becomes 1. And we're going to be multiplying it by -1 to invert it. So all the positive values will become negative value and all the negative values will become positive values. Using that, we will be moving in the opposite direction now. And after that, we can hook this up into the same branch node, and that works perfectly fine like that. And then all we have to do is, after we set the is moving back, we're also going to set our start position back to being our current position. So we'll get the actor location. So that way, when we start moving back, it's comparing with this little code here. It's comparing against the location where we were at when we went back. Now, there is a couple of minor issues to this code which are going to be difficult to show off. But before we do any of that, let's actually check whether what we've made works or not. So I'm going to select this one over here, and I'm actually going to delete this other one because we're not going to be using it. We want to make sure that our max move distance is actually a public variable so that we can change it. And let's add that to 500. So after 500 units of movement, it should go the other direction again. And again, since I'm recording, my PC doesn't really like it. This is very low frame rate. And that didn't really work, did it? And the reason that didn't work is because we put the -1 multiplication a little too late into the chain. What we should be doing is we should be getting the actor location and making a extra plus here and hooking that up this way. So what we'll be doing is, hopefully this makes a certain amount of sense to all of you. What we did before was we got our new location and then multiplied by -1, meaning that it's going to teleport to an entirely different location. What we want to multiply by -1 is just the offsets. And then we add that to the current actor location, and that is the proper code that we want. As you can see, it's always important to keep testing whatever you're making and not just make everything and assume that it works, because a very small little mistake can easily slip into your work. And now, after all that, we can see that it's working. It's going back and forth, 500 units one direction, 500 units into the other direction. Now, there is a tiny issue, that being that over time this thing will start drifting to either the left or the right side. On average, that should cancel out and it should remain in roughly the same place. But on average and should maybe, those aren't really words that you really want to get used to using as a programmer. So we want to make our system as solid as possible so that it doesn't actually do that. Because right now, we're just setting the actor location and it can very well overshoot our maximum move distance. And then that becomes the new starting position to calculate its move distance. And if it just every single time overshoots by 3 units on the right and only by 1 unit on the left, every cycle is going to be 2 more units to the right. That's very much a possibility that could happen over time. So what we'll do instead is when our distance check here ends up being true, what we do is we manually set the actor location again. So we set the actor location to being our starting position, which we can just copy and paste. And to that, we will add our maximum move distance multiplied by our movement direction. And this way it will always exactly be set to its maximum movement distance when it reaches even just a unit or 2 beyond that distance. Now, here we have the same issue that we had before. I'm just trying to get all these nodes into a somewhat readable place, by the way, where we actually need to put in a branch to check whether or not we're moving forward or backward to multiply this value by -1 or not. And here we start getting into, okay, we're doing the same thing a number of times, which is less than ideal. That's not good programming practice. So what we'll do instead is we'll make something in form of a variable that can do that for us. So we'll make a, let's call it invert float, something like that. Obviously, there's going to be a float value, which by default we'll set to a value of 1. Then we can delete this second set actor to location in our branch here. We can actually remove this branch altogether, and we can simply multiply this instead of by -1 by our invert float, which is a bad name for the variable. Because when this is 1, that means that it'll be moving forward. And when this is -1, it will be moving backward. And now we suddenly don't need a branch. We just need to update the value of this thing, which we can simply do in the same way that we updated the value of our bool here at the very end, which is getting a reference to it, setting it, and simply getting a reference to it and multiplying that by -1. Meaning that if this is set to 1, it's going to be set to -1. And if it's set to -1, negative multiplied by negative becomes a positive number. It'll become 1. And now we can get this and multiply that by our invert float to create the offset in either the positive or negative direction from its starting position. And this will now number one, make our code a little cleaner to read because we don't have a bunch of branch nodes all over the place, which is always nice. It makes it easier to eventually like compartmentalize this code into different functions if you would want to. And it's just generally better practice to do so. So now this should work fantastically. You're not going to be able to see much of a difference here when we run the game because, again, this is very much something that would drift out of space in a long time. So while we might not see a exact difference in behavior right away, we've just improved our code by quite a bit, from being functional but maybe a little iffy to actually being quite solid and workable. And I think that will be plenty enough for today's video. It's been quite a long one, but it's very important that you understand the basics of what we have done here today, adding all these nodes together and doing the math that we did. Even if you don't understand every single step that we've gone through, feel free to watch through the video again a second time and try to understand the things that you might have missed out on, and at least get a general feeling of what we did and why we did it. Next time we're going to go into a little deeper with more blueprint stuff, and we're going to fix that issue that we saw at the start of the video, which is also going to be present with this pushing block, actually. And that is the glitchiness that happened when we ran into them, which, yes, the frame rate for this is really low at the moment because, again, my PC is not a fan of rendering this while I'm also recording. But you can see this glitchiness, that's no good, right? And that's got to do with some collision. So we're going to expand the blueprint there to do things regarding its collision. And we're going to talk more generally about collision itself. Let's talk about collision, because we've been making some small things for a 3D platformer obstacle course game, but we had this issue here. And this has to do with collision. And as you might be able to tell, when I'm moving, I actually don't see this issue being a thing. It's only when I'm standing still and getting pushed around by the collision that the glitchiness happens. And that is because the character only calculates collision when it's moving, just to save on resources. We're going to fix that first, and then we're going to get into a little bit more theory and technicality on how collision works and what all you can do with it. So first things first, coming up here to our blueprint third-person character, the thing that got provided to us by the template that we have used. We're going to go into event tick, which, as you recall, runs every frame that the game is active. And we're going to use this to move our character a tiny amount left and then a tiny amount right again. That way, it will always be moving, and as such, that kind of collision check will always be done properly. It's a little bit of a hacky way of doing things, but I personally have not found a better, more convenient way to do it. So the way we do that is we get our character movement, and last time we used set actor location to move a actor around. This time, because we're using the character movement, we're going to do something slightly different. Instead, we're going to use the move updated component node. This will take in a delta, which is just the offset from its current position where it's going to move to, and a rotation. The delta we're going to set to a very small number, something like 0.1 in the x and the y. We're going to leave the z alone. For the rotation, we're going to get the actor rotation and just plug that into there so that it always keeps the rotation it already has. And we want to make sure that sweep is set to on. When you set sweep to on, it will actually check for collision before it starts moving. So what it'll do is it'll check for your collision, which is this capsule component over here, and check if that moves over to my new location. Am I now overlapping with any other collision? Because if so, I actually can't move there. If you don't turn on sweep, it won't do that check, meaning that you will be able to do things like clipping through walls a lot easier. For this, we do need to have sweep turned on. But now we will always be moving in a diagonal line very, very slowly at a speed of 0.1 in X and Y directions. So what we want to do as well is we want to copy over this component, and then immediately after we've moved into that direction, we're going to move into the negative of those same values as well. That way we won't actually be moving, but the collision will see us as if we are moving and calculate things a lot more accurately. And you will see now that when I run into this and I stop moving, we actually do get pushed around as we should be. And let's test it out with this block as well. And as you can see, it works perfectly fine now. That's a little bit about the trickiness of how collision can work in Unreal. It can be a little bit iffy to work with sometimes. Now let's talk a little bit more about how collision actually works and what we can do with it. Because if we go into our pusher blueprint and we select a cube over here, we can come down to the collision settings over on the right hand side here, and we have a handful of different options here. Number one is simulating generates hit events. There's two different events to do with collision in your actors. That being the overlap, actor begin overlap. There's also a component based version of this, and an event hit. These two are very, very similar in a lot of different ways. Because the hit event will run whenever you collide with a solid collision that has this box set to being true. It comes with a bunch of information like which component of your actor collided with the other actor, what the other actor is, what component of that actor you collided with, and so on and so forth. They're pretty self-explanatory as to what they all do. The overlap, on the other hand, is something slightly different, because a collision can be set to either block other collisions, overlap with other collisions, or ignore other collisions. And that is done through the collision channels. So if we open up the collision preset here, which is set to block all dynamic, we'll see that we have a bunch of settings here of how this object's collision, which is a world dynamic, interacts with all the other existing collision channels. In this case, it's set to block all dynamic, so it's going to be blocking everything. And there's a bunch of different presets here that you can use, but you can also go with a custom route, meaning that on every single one of these channels, you can now say, actually, I want the camera to ignore this. And now everything that is looking for collision on the camera channel, such as this camera boom, which is part of our camera system that the template provides us with, is going to ignore any collision to do with this thing. I'm going to set the collision with pawns to being overlap. This means that it's not going to be a solid collision, so I can actually move through it. It's not going to stop me from moving through it. But instead, as long as this generate overlap event is turned on, that will then allow me to go into my event graph and here say actor begin overlap. And there we can do something. And for now, I'm just going to add a print string, and that's going to say overlap started. A print string is a very easy way to test whether or not a certain piece of your code is actually getting executed, or what a certain value is in your code for debugging purposes. It does come with this little warning here, development only. It's not meant to be used to put things on the screen for your actual game. That's what widget blueprints are for, and we're going to get into that a little bit later. And in much the same way as we have a actor begin overlap, we also have an event actor end overlap. And I'm sure that you can tell what this is going to do. This will run whenever we are overlapping with something, and then that something stops overlapping with this actor. So this will be overlap ended. Now, going into our capsule component for our character here, and going into the collision here, we can see that the collision preset is set to pawn, which means that its object type is going to be pawn, which is the thing that we changed to using the overlap collision instead. Which means what's going to happen now is when I run into this thing, it's no longer going to be pushing me around, because it's not set to block pawns. Instead, it's set to overlap with pawns. And it's going to print something to the top left of my screen when I either enter or exit that overlap. So let's see if that's actually the case. I can just go over here and see this collision is still working as intended. But then when I go over to this, I can actually walk through it. And as you can see, overlap started. And when I exit, it says overlap ended. Now, that's not a very good use for what we're doing here, of course, because this thing is supposed to push us around. So we're not actually going to be doing that. So let's go back into the BP pusher here and set pawn back to blocking. And it's important to note, actually, that this code will work from either direction. So right now I have it on the BP pusher, but I can very well also put this into my third person character here. And you can only have one begin overlap event per blueprint. So let's fix that real quick. This will still work because even though I don't have this capsule component set up to be overlapping with anything, the engine still knows that we need to overlap with these two different objects. And that overlap event gets generated anyway. And both of the involved parties can then use that in their code. But this is a rather useless example, right? Because this push-up is supposed to be pushing us around. So obviously we want to go back in here and set this back to blocking the pawn rather than overlapping with it. And we don't actually want to just print a string, and we don't need the extra and overlap here. What we're going to do instead is we're going to make a coin that we can pick up. So let's make a new actor, which we can do by right-clicking and making a new blueprint class of type actor, and we'll call this BP coin. Let's open that up and just add a simple sphere for the visualization for the time being. Now we could just set the collision for this sphere to overlap with the third person character, and that would work great. That would be entirely a correct way of doing things. But there's actually something else that I want to show you, because we have, if we type in sphere, we have a sphere collision component. And as a matter of fact, we have multiple collision components. We have a box, the capsule, which we've already seen. That's the one that's used in the actual character blueprint. And a sphere. And these things, as you will see, have this outline to them, which is a very nice visual way of showing how big the overlapping collision will be. So let's make that just a little bit bigger than the coin itself. And then if we go down to collision, the preset for this is set to overlap all dynamic. And if we look what that means, it literally means that any object that it could be interacting with, it's going to overlap with. Meaning that it's going to generate an overlap event. So let's do a little something with that, right? Let's go back to our third person character. And for now, just add a variable that we're going to call coins. And that's going to be a integer, because it's going to count up entirely in whole numbers. And we're going to make that public for now so that we can easily see the value going up as we play. In the event graph for the coin though, we're going to ignore the begin play and the tick, because anything we want to do with this has to do with the overlap. And when this actor overlaps with another actor, we want to destroy the actor. And we want to destroy the self. And now we can start putting some of these inside the level. Just put a couple of them around as easily as that. And we can start picking them up and we see them disappearing when we run into them. But you'll also note that the sweeper over here also triggers them to disappear, which is not something we want. We only want the coins to be destroyed or picked up when the player itself touches them. And that touches on something that I'm going to make an entirely separate video about soon. We've had a handful of very long, very information-dense videos to start the series off, so I'm going to compartmentalize the information a little bit more going forward. I'm just going to show you now. If you don't understand what's going on here, I will make a separate video on this very soon. Because what we're going to do is we're going to take the other actor from our event begin overlap in our coin, and we're going to cast that, and we're going to cast it to the third person character. Essentially what this is doing is it's checking whether or not the other actor is the player character in this case. And then it's creating a variable that we can use that has a reference to the player. Because from there, we can see, hey, we can access the coin variable on the player from this coin. Again, if this doesn't make a lot of sense right away, don't worry about it. I'm going to make a more in-depth video explaining how this works. But we can get the value for coin, and we can simply say increment integer, and that will add a 1 to the value of that variable. And then after that, we destroy it. So now we will see we can still pick up and destroy these coins. But when this sweeper comes in contact with them, it will actually just pass right through them without destroying them at all. And if we go and select our third person character here, and we go into the details panel to see how many coins I've picked up, right now we have got this set to 3, and let's lock this so it remains visible as we continue playing. The moment I pick this up, it becomes 4, and then it becomes 5. So we have a simple coin pickup system now as well. Now, one last thing that you might want to do is you can forego this entire casting if you wanted to. It's generally better to keep the code for a specific object's purpose on that object itself. What that means is that I could add that code on the begin overlap here and test if the actor we're colliding or overlapping with is a coin, and then add the score adding functionality to this actor. That would be an entirely fine way of doing things as well. Generally, that will end up with the character having literally all the code in the game on it, and every other object really not doing too much. But it does avoid you having to use the casting if that confuses you. I want to show you one last thing to do with collisions before we end off this video, and that is making your own custom collision channels. Because maybe, for whatever reason, we want to set this to being a custom collision setup, and we want to actually just ignore everything. And we want the player to be able to see specifically this object. For that, we can make a new custom collision channel. And for that, we can go into the project settings. And if we just look under engine and then collision, we can make object channels or trace channels. We'll get into traces a little bit later, I think. For now, what we want to make is a new object channel. Note, you can only have up to 18 custom channels, including both object and trace channels. So you can have 10 and 8, or 17 and 1, or 1 and 17, or 18 and 0. But both of these together, you can only have 18 of them in total, which in general is plenty enough, because you wouldn't usually make a collision channel just for collision for one specific object. What I'm going to show you right now wouldn't really be how you make an actual game, but let's just get into it anyway. We're going to make a new object channel, and we're going to name that just something simple like coins. And the default response, so unless we set it to something else, everything is going to ignore the coins. And now you will note when we are back in the BP third person character, we have a new collision channel here that we can set. And it's set to ignore because everything is by default ignoring the coins. But let's change this to a custom setup and set it to coins overlapping. And now we have a situation where the coin is set to ignore literally everything, so including the pawn, which will be our player. But our player in the capsule component is set to overlap the coins. So what will actually happen here? And what will happen is that the leftmost choice that you have made is the one that's going to take priority. If we have one thing set to overlap and one thing set to ignore, it's going to ignore. If we have one thing set to block and one thing set to overlap, it's going to overlap. And then obviously if we have one thing set to blocking and the other to ignore, it's going to also ignore. Which we can demonstrate here, because when we walk into these coins, nothing happens because the overlap event isn't getting triggered because the coin itself is set to ignore, which takes priority. And as a quick note I thought of afterwards, the reason we're not walking through these coins is because the mesh itself also has collision set, and the collision for the mesh is set to blocking the pawn. So when we go over the sphere collision, that's ignoring us, but the moment we touch the actual mesh collision, that is then blocking us. So we do gonna make sure that the pawn here is also set to generate overlaps. And we make sure that our object type is set to the coins layer as well. And now we have control on the character basis on whether or not we want to be able to overlap with it. Because if we now set the coins on here to being ignored, it's going to not care about the fact that the coin might be thinking, oh, I want to overlap with pawns, because this pawn is saying, no, I'm entirely ignoring anything on the coin layer, which I can show off very easily here. So now still nothing is happening until I set this specific blueprint to overlapping with coins, at which point our coin collecting works again. So now we have a opportunity to create other pawns like enemy AI, which won't pick up the coins because they will be ignoring the coins channel. Only the player character itself will actually have the coins set to overlap, meaning that only the player character can now pick them up. Working with these different options in collision is a fundamental piece of creating games, because this is the way objects will interact with each other. Very rarely will you have two objects interacting with each other that don't necessarily have to do with collision. Usually when they're interacting with each other, it's either because they are bumping into each other or they are in each other's overlap collision, meaning that they need to communicate something to each other. Next time I'm going to take a little bit of extra time to dive a tiny bit deeper into what this casting node actually does and how it works and what you want to do with it, because this is a very important next step. Now that we have actors interacting with each other through collision, we also want to know how we can actually use information like variables or even events and functions that are on these other actors that we are interacting with. And that is where casting comes in. So in a previous video, I used this casting node without explaining too well what it actually does and how it works. And it is a very important thing to understand. So we're going to make a quick standalone video on this. And a casting node does two very important things. Number one, it lets you check whether or not an actor that you have in your code is of a certain specific type. We've talked about actor types before, that being actors, pawns, characters, and all of the derivatives that you can make of it yourself, or the children that you can make. And right here we are in my BP coin, which is the blueprint for my coin. And when we overlap with something, that simply gives me a actor reference. The only thing that this knows is all of the information that is in the base actor class. So that is things like the get actor location we can use with this, because a base actor is all we need for that. But we need some specific more information than that, because we need information that is not stored in the actor class. Instead, we need information that is stored in the BP third person character class inside of our blueprint for our character that we have here, because here we have an integer for coins. So how do we get this generic actor to transform into a reference to specifically the BP third person character? And that is what a casting node does. A casting node takes in an actor, it checks, is this actor of a certain type? And if it is, you can use it to create a new reference to specifically that type of actor, allowing you to then use and get access to the information that is specific to that type of actor. In this case, the variable for coins. You don't even always need to use it to get access to information inside of an actor though. You can also very easily use this to check whether or not a certain actor is of a certain type. Because we have two execution pins here. The top one will execute whenever our cast is successful. So whenever the input matches the type that we're looking for. But if we put anything else into this, the cast will fail. And we actually have a separate execution pin for that. So we can print a string and we can say failed to cast. We can print that out, right? And if you've been following along with the previous tutorial and you're confused as to what might be different for you, I have set the object type for the coin back to world dynamic and everything to overlapping, so that this overlap event will be generated by something that is not our third person character. If you don't know what the hell I'm talking about there because you didn't see the last video, don't worry about it. Because now, when I run into these things, I can still pick up the coins, but when this sweeper runs over one of them, we will see that it will have failed to cast, because it's trying to cast this BP sweeper into a BP third person character, which is entirely a different kind of blueprint, so that's not going to work. There, however, is one exception to that, and that is if I'm trying to cast to the parent of whatever this object is. So that sounds really confusing, right? Let me explain. We've talked about the actor hierarchy before, very early on in the series, where we explained that a actor has a child called a pawn, and that pawn has a child called a character. We made a child of that character, and that is what BP third person character is. So when I try to use my reference to what I know is a BP third person character, the engine at this point in this node still doesn't know that until after we've cast it. I can cast this to any actor that is also a parent of the BP third person character in this case. So if I wanted to instead cast to character, I could do that and that cast would succeed. If I wanted to simply cast to the pawn, I could also do that and this cast would also succeed, even though at first glance it might look like, but this is a BP third person character. It's not a character or a pawn. So why does that cast succeed? And that is because it actually is a character and it actually is a pawn. And that is because this casting works on anything above what we're specifically looking for in the hierarchy as well. And we can make some sense of that, right? Because the reason we want to cast is to create access to information in a certain blueprint. All the information for a character is also already accessible in my BP third person character, such as the capsule component and the arrow component and the mesh component and the camera boom component and the follow camera and the character movement components. All those things we have in my BP third person character because they are in its parent class, in the character. And in the same way, the character, and by extension my BP third person character, have something called an AI controller or a player controller. And they have that because those are established in the pawn blueprint. So when I cast this actor to the pawn, I will get a reference to it as if it was just a pawn, nothing more. So at this point, I can't get the coins variable out of it anymore because the engine doesn't know that this pawn is also a BP third person character. Why would you want to do that though? That is because in general terms, it is better and more performative to only cast to specifically what you need. If I only needed the capsule component out of my BP third person character, it's better to cast to just the character than to also cast to the thing that has a bunch more information accessible as well. It's not a very big difference, and by and large, if this part confuses you, I would entirely just ignore that optimization because it's not that important. So we could, if we want to show that off a little bit better, chain these things together. So really what we're doing in this chain is we are taking a generic actor and then we're upgrading the reference to it to a pawn. And then we're upgrading it to a character. And then we are upgrading it to a third person character. It's just that before what we did is we took out those two steps because the engine can do that math for itself and immediately go from actor to third person character. I remember when I first got started in Unreal, this whole casting business really took quite a while to wrap my head around. So if you still are not 100% on anything that I've just said, that is entirely understandable. With time, practice, and experience, you will run into issues, misunderstanding it, doing it wrong, and eventually you will start learning it a little bit better. And you can always at later points come back to this video and listen to this explanation again, maybe when you have a little bit more wider knowledge about the engine, and maybe at that point it'll click a little bit better. So far we've made a couple of things that we've been testing out in this little example level. But at some point in a game, you're going to want to make your own levels. So let's talk about that today. If you want to make your own levels, there's two ways to do it. Number one is just right-clicking and adding a new level asset. And let's just call that a level 1. And when you open that up, you will see absolutely fucking nothing. This is an empty level, which can be a pretty decent place to start from if you know that you're going to want to do everything entirely custom anyway. What we're going to do instead is we're going to come up here to a file at the very top of the screen, which is just off the recording, but it's on the top right. And then we can just create a new level, which gives us a couple of options. A open world, an empty open world, a basic level, or a empty level. By default, you're making an empty level, but we're going to be making a basic level. This is set up with a directional light, some exponential height fog, an atmosphere, a skylight, a sky sphere, and volumetric clouds, which is, of course, the clouds that you see. And not unimportant, also a floor. One thing that you will note is lacking here is our player starting location. So we need to actually put that in ourselves. And when we play this, you can see we now have the start of an entirely empty level that we can start adding our own things to. So first things first, I'm going to remove this floor over here because we're going to be adding our own floor. Using the Place Actors panel, if you don't have this, you can come up here to Window and Place Actors and just enable that window here. And this allows you to place a bunch of either your own actors or a lot of actors that the engine provides you with. And we're going to be using some of the geometry actors. These are very nice to block out your levels. Eventually, usually you'll be replacing most of these with custom meshes that you've made yourself, which is an entirely different series in and of itself, making 3D models. But this is a good way to block out your levels and test out things before you make everything very fancy looking. So we're going to start with adding a block over here, and we'll add that to location 0, 0, 0, so that it's at the very center here. And actually, let's lower this a little bit so the player can stand on it properly. And what you probably want to do here, we want to go into the front perspective here, and we want to enable our snapping to grid. And let's set that to 100. So now we can easily move it down 100 units. And if we start playing the game, we're now on the block that we just added in. It's not quite a good game, is it? Well, this is where something interesting comes in. Because with these geometry actors, so the box, cone, cylinder, curved stairs, linear stairs, spiral stairs, the sphere, all that kind of stuff. If we have that selected and we go into brush editing mode, we can actually start editing these in any way we would like. So we can create this to be a little bit longer, and we can also make it a little bit wider. Let's do 200 units wider on both sides here. And as easily as that, we have a bit of a longer walkway. So now we've got a place to walk on. I'm here from the future to tell you something that I skipped over in the main recording here, and that is using these geometries, you can just use them to create blocks. You can also set the brush type from being additive to being subtractive, which means that when it overlaps with any other box brush, it will cut out itself from that brush, which allows you to easily make things like a hole in another platform. As well as you can make these boxes a little bit larger if you want to. And then if you go inside it, of course, you don't see anything because you only see the outside. You can turn on the hollow property, which then makes your entire box kind of like a room. And going to the outside, we even can set the thickness of the walls. So combining that with having some boxes which are set to being subtractive, you can easily make a room and add some windows into it and that kind of stuff. We're not going to be using that anymore in this video, but going forward later into the entire course, we might end up with a block out for a level that uses this kind of stuff. So I don't want you to be confused as to how I actually ended up doing that. And once we've done that, if we're back in selection mode, we can simply, as we talked about in the interface video, maybe copy this over and raise it up a little bit. And maybe this is a little bit too much, but we can see, can we make that jump? I can already tell you, we're not going to be able to make this jump, like, at all. So maybe what we do instead is we increase the height even more. We put it over that way. And let's add one of our own actors, because we made this pusher block before. And this thing can, of course, push in literally any direction. Let's set the snapping to 50 so that we can actually put it exactly in the middle of our walkway here. And this is a jump that we should be able to make, right? In theory. So we can set the movement direction to be in the up direction. So just going up and down into the Z. The movement speed, let's keep that at 10. And the movement distance, we can check we're at -400. We want to be moving up to about 500 in the positive, so the movement distance will be 900. And now we'll see a very slow moving elevator, effectively. And we can make that jump. Probably want this to be a little bit faster, so let's set this to, I don't know, 60? 60 seems about right. Let's see, that's a little bit better. Of course, right now, we can't make it on the first cycle, so we're going to have to sit here, and that's not particularly good level design, so you want to be able to time this a little bit better, because this is very tedious and very boring to sit through for a player. So you either want to make it slower so the player can actually get to it, or you want to make it faster so you don't have to sit here as long as we are right now. Or, as we'll talk about a little bit later, you want to make something that prevents this from moving until you're closer to it. Anyway, this is now one of our own actors combined with some of these block meshes to make a rudimentary little bit of platforming. So let's add on this platform here. Let's make this one a little bit longer. So go back into our brush editing, because we're going to be adding a couple of obstacles in here. Going back into selection mode, let's put in a couple of these pushers again and put them off to the side here. And this is going to be moving in the Y direction. So let's set the direction to being 1 in the second field. 50 speed, and then we wanted to move from about -500 to about +500. So let's move it a distance of 1,000 units. And then put another one, I don't know, at 5,000. So that's 1,500 units to the X. And then in the middle of those, so that should be around here, put one on the other side. So we want to put this one on +500 and make it move in the negative Y direction. And let's change the movement speed around a little bit to make it a little bit more intense. So this one's going to be moving at 40 and this at 60. That just prevents these from syncing up too much. And I don't know if I've shown this before, but what you can do if you're using a player start to spawn in your player, you can actually right click anywhere in your level and just play from there, and you'll spawn in there. And you probably want these to be a fair bit faster. So let's set this speed to like 150, and then this one to 180, and this one to 120. And then we can again play from here and see what that feels like. It feels pretty good, and we're trying to dodge these, which is relatively easy, but hey, this is the first level of the game. Of course it's going to be easy. And then we can have another jump into another platform that's maybe a little bit lower down again. And here we can add in our sweeper actor that we've made. So we just put that in here, and there's nothing much here that we really need to be putting in. So we can add in a sweeper here, and maybe another one over here. And then let's make a little platform here, going back into the brush editing mode, that we can use as like the victory platform. We don't really have an actor set up to end the level with, like a trophy or anything. Maybe we'll do that at some point. That's just a little bit too far away probably still, so let's put that over there. And now we can play through the entire level if we wanted to. So let's try and make that jump. No, we still cannot. So I'm going to just cheat for a moment here. I'm just going to start playing from here. So we can actually make that jump in time without having to do anything too weird or fancy. And this thing in general probably needs to be a little bit faster because it's just boring standing on this. And now we're trying to weave in between these, which is really, really easy still. And then we can jump down to this. And this also, these probably need to move a little bit faster, but there's a lot of fine-tuning in the whole level design thing. And now we're at the end of the level. Now, is this the best level that you can ever create? No, it's not. It's very basic and rudimentary and just a general block out of the level. You're going to need to tweak a lot of the variables on the movement speeds on these things and how far apart they're spaced out, and maybe you need to make more than just 2 types of obstacles here. But as you can see with these pushers, you can use them creatively, right? I'm using them here as an obstacle, and this one, it's the same actor, but I'm using it as an elevator. So something you could potentially do, and let's just try that out real quick, is move this thing over a little bit and copy over one of these sweepers. And if we make this like twice as big, and we move over and flatten this thing out, kind of make it into a bridge, right? So let's see if we play from here. It's gonna be a little bit scary to make this jump, but this could be a very interesting implementation of this rotating platform. And yeah, that definitely needs to be moving slower. Yep, we can't make that jump. So we can go into the rotating movement component here, and the rotation rate, let's set that to something like 7, about half of what it was before. And now we probably should wait for it to rotate around, so I'm just gonna stand here and wait for that for a moment. We're almost there, almost, and we can miss the goddamn jump. Okay, let's try that again. Okay, let's not miss the jump this time. And now we need to make it just in time to make this jump, and that makes it a little bit more exciting, right? I think that is actually a very fun obstacle. And once again, we didn't need to program anything new. This is an actor that we're using here to try and sweep the player off the platform, and here we're using it as a rotating bridge. So being creative with the implementations of what you've already programmed is a very important part of designing a level. And of course, while programming these things, keeping in mind that you want to be able to use them in a wide range of different scenarios and allowing you as a level designer to do that with the code that you've written, also a very important thing. One last thing though, you saw me fall off, and that was just like, I had to reset the game, right? That's not that good. So what you can do is come up here to a window again, which again, it's just off my recording, but it's at the top bar here. And we can open up our world settings. And that has a variable here called kill Z. Any actor falling below this level gets destroyed. By default, it's set to a very, very low elevation. But if we're looking at where our actual actors are in our details panel, these are at about -500. So going into the world settings, if we set this to -1000 and we just jump off here, you will see that when we hit -1000, we die, which is potentially worse because now we're stuck in a game without a player. So as a little bit of a bonus before we end off this part of the tutorial series, we're going to go back into our third-person blueprint. And if we right-click in our event graph and we type in destroyed, we get an event destroyed, which is called when the actor has explicitly been destroyed. So if we add that, this code will run whenever the actor gets destroyed. So when we kill it. And here we can open level either by name or by object reference. Let's do the object reference for now. And we can choose a specific level out of that. But what we can also do is get the current level name, which apparently we can't get the current level asset. So in that case, we're going to just open level by name instead. So now when this actor, which is our player, gets destroyed, we look at what our current level name is and we open that same level. That just resets the level. That's a really easy way to reset on death. So now when we jump off, we can see the level resets when we die. We have the basics of a level, but sometimes you need to animate things within your level, or you want to make a cutscene, or you want to do something a little bit more involved than just moving a block back and forward, which we can do through simple programming, right? That is where our sequencer animations come in. So let's go back into our content folder here. And if we go into our cinematics, we can make a level sequence. And we're going to make a little intro cutscene, kind of like Mario Galaxy or Mario Sunshine, that kind of thing, right? Kind of in that style, where we show off the level before we actually get to play it. So let's call this intro animation. And we can drag that into our level. It doesn't really matter where you put it, but I like to put it at the places where they get triggered. So we're going to put this one at the start. And if we double click that asset, we open up a new window here, which is the sequencer window. Here we can drag in actors from our hierarchy and animate things about them. Pretty much anything you want to animate about them. So what we're going to do is we'll be adding a couple of camera actors. So let's add a camera actor here first and put that one somewhere around here, maybe-ish. And if you want to, specifically for camera actors, some other actors it also works decently well with. But if you want to move it around a little bit better than like this way, you can actually right-click. And what you can do is we can pilot the actor. And now we can move it around as if it was just our view. So let's put this one in here. And it automatically makes a keyframe for the first position. So let's click on that. And then move about 60 frames. That should be about a second. Oh, it's set to 30 frames per second. You can set the frame rate for the animation here. So let's set that to 60. If your game runs at a different frame rate, this will just like match up with speed. So if you're running at 120 frames per second, this animation won't play twice as fast. It's just for you as a developer to have a reference of, okay, 60 frames per second. So if I set this next keyframe at frame 60, that will be 1 second. Matter of fact, let's actually make it a second and a half, 90 frames. And we can just move our camera like back a little bit and click this transform again. And now we can see that our camera does this movement, which is way too fast. So let's get that keyframe and put it at like 240. And that's a little bit more like what we expect it to be. But you can feel there's a little bit of easing in and easing out of the movement, which oftentimes is what we want. But in this case, it's actually not. So let's right click here and let's set the interpolation mode to being linear. That means that it will not have that easing. And now it's just a linear motion moving backward. And the most wonderful thing is, if we can add a track here, we can make a camera cut track, to which we can add a bunch of cameras, which means that when this animation plays, we can automatically cut from one camera to another to make a cutscene. Something a little bit more cinematic, you know? Showing a little bit of this camera movement and then showing a little bit of that camera movement and cutting back and forth, and maybe with dialogue, cutting back and forth manually between two cameras, that kind of stuff. So we can add a camera and we can just an existing camera actor, which is this one. And now we can see that we're using this camera actor for here. So let's add a extra camera actor. And what we can actually do, because a camera actor is kind of supposed to be a gameplay camera. If we specifically are making a cutscene, we can use a cine camera actor, which has a couple of more options to make things look a little bit more cinematic. So for the second one, let's add a cinema camera and pilot that. And as you will be able to see, by default, this one is a lot more zoomed in, which is not what I want at the moment. So we can set the focal length, as it's called, to something a little bit lower, so that it's a little bit more zoomed out. And this is a little bit more of what I am looking for. And this comes with a bunch of different lens settings as well, which can make things look much more interesting and cinematic, if that's what you're going for. So let's go to the end of our previous animation and add our cinema camera actor into our sequencer as well. And we want to animate its transform component. And let's do another like 200 frames or so, moving in this direction and rotating a little bit, something like this. Putting in another keyframe here, and now we can see that's rotating around more or less in the way I would like. The movement itself, though, is still in a straight path, which I can see if I stop piloting. The movement itself is in this straight path that we see here, which might not be what you actually want. So let's increase the length of this cutscene to actually be long enough in total. And now let's select our transform, open up that menu here and get to our location. And specifically, we want to change things a little bit about the Y location. So let's select that track specifically. And we can show the animation keys in the curve editor instead. So this shows the movement as a curve that we can actually edit a little bit. So if we, for now, make this full screen and we select one of the keyframes, we can set this broken tangents cubic interpolation, which allows you to change the tangents, which are these little handles over here, independently from each other on a keyframe, which is very nice. And then we also want to toggle weighted tangents for cubic interpolation modes, because that allows you to actually make the tangents longer than usual. And with that, we're going to put that back down into our window here, because now we want to be able to use that to make this thing move back as well, without needing to add any more keyframes. So we can zoom out a little bit to see what our curve looks like. And now we can also see that the path in the viewport here is curving a little bit. And playing with these two tangents both allows us to eventually get the kind of curve that we're looking for. So going back into the sequencer itself, we also get a little preview of the camera itself here, which is very nice. Now we can see that it also moves in a curve which works really, really well with its rotation. And of course, we're going to add a camera cut when this thing starts moving. So we pull back our first camera here, and then in our camera cuts, we add a second camera, which is going to be the cinema camera actor, and we'll cut from that actor to this actor. And let's add one more that just does a pullback of the entire level. I think that's quite fun. So we add another cinema camera actor here, which we add to our sequencer. And you can see when we do that, we actually automatically start piloting it as well, which is rather nice. And again, we want to zoom this out a little bit more. Matter of fact, maybe we want to actually zoom this out even more, because we want to be able to capture the entire level in one go. And we put in a keyframe here on the transform, and then we pull out even further, adding another keyframe to the very end. And again, this red line, you want to extend that to the end, because that's actually how long this sequence player plays for. And we're going to add that as a camera cut, which in this case, I think this is actor 8. Yeah. And now that will cut over to this camera as well. And if we stop piloting that now, we can go over to the actor for that sequence player in our viewport, and we can turn on autoplay. I don't think it's turned on by default, but I tested this a little bit before. So you can turn on autoplay and set whether or not it should loop. In this case, we don't want it to loop, of course. But if you do want it to loop, we can say it needs to loop indefinitely. So it's always going to keep looping. Or you can make it loop an exact number of times. So we can say you loop 1 time, or you loop 5 times, or you can even loop like 27,000 times if you wanted to. But after that number of loops is done, it's going to stop looping. Again, we don't want our thing to loop. We can set the play rate. So if we've made all of our animations and they're good as far as the proportions of the speeds goes, but maybe it's entirely a little bit too slow or a little bit too fast, you don't need to reanimate everything. You can just set the play rate to be higher or lower. The start offset is pretty self-explanatory, I would imagine. And then we can also say that it should start at a random time, which is something that I honestly never use. And there's a bunch of different other things as well that we can do. So if we start our level now, we can see as soon as we start a level, we have this little cutscene that plays that shows off the different obstacles in the level. And then we cut to our actual player and we can start playing the level. There's one little issue though. As those cutscenes are playing, we can actually already move around even though the camera doesn't see us, which we want to disable. So something we can do, let's go back to the start of this animation real quick, and we can add a new track here, and we can add an event track, which will go for a trigger. and add a new key at our current time. If we right click that, we can go into the properties and we can say the event at the moment is unbound, and we can bind this to any actor and any event on any actor in our scene. We can also create a new endpoint, which will create a event in the animation itself. So we can see here intro animation, director BP, create a new sequence event. So let's call this disable player movements. And here we can simply get our player controller and disable the input for it. And we want to put that into the player controller. And then the target is going to be get player character, which gets us a reference to whatever our player character. So that way our input will be disabled at the start of this animation. Let's dock that up here because we're going to come back to this in a moment. And we can check that by just playing the animation itself and waiting, because nothing is restoring our player input. So once this animation ends, which is very nice, we still don't have our input. We can't move, meaning that we couldn't move all throughout that animation because of that event. Well, of course, once that ends, we want to be able to move. So what we do is we go to the very end of our animation here, and we simply add a second trigger here. So we add a second keyframe, we go to properties, event, unbound, create new endpoint, and that adds a second event into this intro animation, and we'll call this enable player movements. And for this, we'll copy over these get player character and get player controller, because with this, we're going to enable inputs. And of course, again, it's going into the wrong pin here. We want a player controller in a player controller and a player character into the target, connect it up to our enable player movements. And now we'll see if we play this, we get the cutscene at the beginning of the level. And when the cutscene ends, our player can move around and play that level. So now we have a Mario Galaxy style intro cutscene for our level. And that immediately, as you can see, adds a lot of production value and a more professional feeling. Even though we're still working with very blocky and temporary assets, it does add a feeling of more quality, polish, and professionalism. So we have actors, we have a player, now we have a level. The one thing that we are still missing is how all of that really comes together and how we can implement our final gameplay logic. And what do I mean by that? Well, in the previous part, if you followed that along, we made this cutscene. But as you can see, during that cutscene and during our just standing around here, this first block is already moving, and by the time we get there, we need to wait for it to move down, and that's just not very good level design. So what we could do is we could make this thing move a fair bit faster, so something like 120, right? We could do that. But instead, let's actually set this to 0, so that it doesn't move at all in the beginning of the level. And then we will dynamically change the movement speed variable through something called the level blueprint. So if we come up here, we can open our level blueprint. And that just opens up a blueprint like any other actor that you might be used to. But this is the blueprint specifically for this level. So we can get any objects in this level and get a reference to it and do some scripting regarding that. So we'll select this little elevator that we have here going into our level blueprint. We can right click and create a reference to that specific instance of that actor. Don't worry too much about the from persistence level. That's about level streaming, which we'll probably get into at some point in the mid to near future. And from here, we can get and set the movement speed, which seems like I misspelled. And we can set that to whatever we want specifically for only this instance again. So all of these actors, which are based on the same blueprint, will not be affected by this. It's literally only this object. And we can set that to, it was a little bit slow, so actually do set to like 110. But now, how do we activate this? Because if we just hook this up to begin play, we're back at where we started. It's moving when we don't want it to move yet. So that's where some other fun things come in. Going back to our place actors, again, if you don't have that, go up to window. You can enable the place actors window here. We can add in a trigger volume. In this case, let's go for a trigger box. And if we put that in the level, we get our box extend, just like we do with a collision box, for instance, in an actor. But this one is specifically meant to be placed in levels. So we can place that wherever we want. This seems about correct. Let's place it around here so that it has no collision with anything else. And then while it's selected, going into our level blueprints again, we can, instead of creating a reference to it, we can call the events that this thing generates. And of course, it has an on-actor begin overlap event, as any actor does. And with that, we now have an event that we can use to enable the movement speed here. If you want to be very thorough and make sure that this only ever happens when the player is overlapping this, for instance, if you have enemies in the area walking around as well, you don't want those to be able to trigger the trigger box. The easiest and most simple way is to just get the other actor pin here and cast that to your third person character blueprint. That way, whatever we put after this will only happen if this trigger box is being triggered by the player character. And now we'll see, again, this cutscene plays, but our block over there doesn't move yet until we trigger this box, at which point it does move, and it does move a little bit too fast. So we can probably put this a little bit closer to there. And now it only starts moving when we really get close to it, and it just starts to go up in time for us to jump onto it. And that just makes the whole flow of the level a fair bit more player friendly. And you can surely imagine that you can use this level blueprint for literally anything that you want. Anything you can do in an actor, you can do in this. And potentially even more, because you have things like these trigger boxes that you can reference. So maybe we want to have a second trigger box here. Let's place that over here. And let's make another event overlap for that. Check if we're overlapping the player character. And instead of playing the cutscene at the beginning of the level, what we can do is we can select this little sequence player over here. And with that selected, of course, we can now create a reference to that in our level blueprint. And from that reference, we can play the sequence player. We can play that animation. So now, instead of at begin play, so we need to turn off the autoplay here, of course. When we start the level, it doesn't automatically play, but when we start going forward, it now plays the cutscene, showing us the level, and then we can get moving with the level itself. And as you can see, the elevator block still isn't moving, because of course what we just added doesn't even interact at all with either of those other two actors in our level. Now, one important thing here is that since we're using a player start actor, and we're not just putting our blueprint in the level itself, we have a hard time getting a reference to our player. So if we want to change something on our player in this level blueprint for whatever reason, that's going to be a little bit tricky, but not entirely impossible. So let's stick with me here. Let's use this trigger box to both make this thing move and increase our player's jump. And then put another trigger box over here to then decrease our player's jump. Again, back to what it used to be. So going into our level blueprint, first and foremost, let's put this trigger box up here somewhere because we're not going to be using that anymore. And we can add an overlap event. And again, we're casting to the third person character. And as such, we don't need a direct reference to our player character because we're checking the other actor here. And the other actor is just a generic actor reference. Then casting is just checking, is this generic actor reference, does that fit within this specific type of actor? We've talked about actor hierarchy before. And if it does, so in this case, if it is the player, this output pin then becomes a reference, a variable to that specific type. So in this case, BP third person character, meaning that while we cannot get the character movement components from this reference, if we do the same thing here, we can get the character movement. And that is what allows us to change the jumping. So let's do that here as well, and get the character movements, which is all the way down here. And from there, we can get the Z jump velocity. And let's put that into a variable so that we can save it and reset it back to whatever it was in our next trigger box. That way we don't have to hard code values, and if we change it in one place, now we have to change it in 50 places. Just storing it somewhere to be used later is probably a better idea. So we can right click this pin and just simply promote to variable. It's automatically called Z jump velocity. I think that will do nicely. And we will also set the jump Z velocity. And here I actually got to check what the original value is to know what we should set it to. So let's go check that in our third person character real quick. In our character movements, if we just type in jump Z, our jump Z velocity is 700 by default. So let's set that to 1200 here. So now we'll be jumping almost twice as high after we have overlapped with this trigger box. And then with this other trigger box, which again, this is the trigger box that will increase our jump height, and this is the trigger box that then will again decrease that jump height, which actually, let's make that a little bit wider so the player can't go like past it and break the rest of our level. We'll just set the jump Z velocity to the variable where we stored it in before. And I'll tell you right now, there is one issue with this code that we have made here. There's one thing that we can do in the level itself to break this system, which isn't great. I'll let you think about what that is for a second, and now let's go play it and I'll show you. So we triggered a cutscene, again, through that trigger box, that's all fine, that works. And our jump is still relatively low, but then when we trigger this, we can see our jump is significantly higher. And when we jump through this, our jump goes back to being lower. So what allows us to break things? Well, I'll show you. I died, so now I need to watch the cutscene again, which that's another thing. You don't want to have to rewatch the cutscene a number of times. I didn't even think about that, but that's definitely another thing we want to fix in a moment here. But what we can do is when this jump height is set higher, if we enter the trigger box again, now that variable we have made has stored the higher value. So when we try to restore our jump height, and I jumped off the level, so that's not great, but I'll just show you here. We go through this, get our jump height set to 1200, exit it, and then when we go back through it, our jump height is already set at 1200. But this little thing here, this temporary variable, is now getting overwritten with that new jump height. So when we then go through this trigger box, we're not getting reset back to 700 because our temporary variable has been set to 1200 now. The easiest way for us to deal with this at the moment is to select this trigger box over here. And when we overlap with it, we create a reference to it. And we simply just destroy this actor at the very end of it. So this trigger box will do what it needs to do and then disappear from the level. That way we can't overlap with it a second time and do some kind of weird stuff. And the same thing goes for triggering this cutscene, right? We don't want to re-trigger this cutscene by walking backwards. So after it's done everything it needs to do, we can simply destroy this actor. So I'll show you again. We trigger the cutscene, and by the time this cutscene is playing, the trigger box that we just triggered already is gone now. It doesn't exist anymore, it has been destroyed. So if I walk back and I walk forwards again, the cutscene doesn't get triggered again, because if we go into F8 mode here, and we show collisions, there we go, that's the trigger box, you can see the trigger box that was here a moment ago doesn't exist anymore. Let's go back into our game here. Now we have triggered our jumping boost, and you can see the other trigger box now as well is gone. So that's how you can use trigger boxes in combination with level blueprints, and of course in a level blueprint, any functionality on any actor that you have made, you can actually access. Like the movement speed we have on this block over here, we could change that through the level blueprint. We can even change the movement distance or the direction if we wanted to. But there's one final piece to the puzzle that you're going to want to understand. But this video has been long enough as it is, so we're going to spin that off into its own separate bonus video here. and we're going to be talking about event dispatchers and how you can link together events on specific instances of objects using your level blueprints. But that'll be next time. So thanks for watching for now. We're starting to build a pretty decent level for our simple obstacle course game here. We've talked about making these actors that we have here, and last time we got introduced to the level blueprints, specific programming for the specific level that we're in. But that video ran a little bit long, and I wanted to talk about one more thing that I want to show you. So we've discussed a lot of pre-made events, and what I haven't shown you yet so far is the ability to make your own custom events. And that's mostly useful for organizational purposes up until this point anyway. Because today we're going to be talking about this bottom category over here. I think the easiest way to tell you that would be to just straight up show you. So what we're going to do is I have our blueprint for our coin here, which actually I was thinking we're using a sphere mesh for this. I think Unreal just has a cylinder mesh. So we probably just want to use that to make it look a little bit more like a coin. It's not perfect, but again, we're not making assets here, we're making just the functionality and the basic principles of the engine. So now that we have a more coin-looking coin, and let's add a rotating movement component to it as well, why won't we? And rotate that at like 25 units? I don't know, something like that. We have a more recognizable coin. And what we're going to be doing here is we're going to go into the event graph, and we have our event actor begin overlap. And when we destroy this actor, this actually fires off another event. And that event is event destroyed is what it's called. So when this happens, this function also calls this event, which is very nice because that means that we can put in something that happens every time a coin gets destroyed. But how does that actually work? And how can we replicate that with our own functions and our own events? Well, that's what we're going to be talking about today. And that is what event dispatchers are. When this function is run, which I can't show you because that's a C++ thing, what it's doing is it has an event dispatcher. So let's call this coin picked up. And this event dispatcher can do a number of different things. If we pull this in, unlike a normal variable, which we can get or set, this one can be called, or we can bind or unbind all, or event or assign. In this case, we're going to call the event dispatcher. So what we do here is when this coin is picked up, this event dispatcher is just going to shout out into the world, hey, I've just been picked up. Anybody interested in what happens when I am picked up? You might want to do your thing now. That doesn't necessarily mean that anything is listening to this actor. It just gives us the capability of telling another actor, hey, you listen to this one. And when this event dispatcher gets called, you execute a specific event of your own. That is basically how the destroy actor to event destroyed works. There's an event dispatcher in here, which automatically calls the event destroyed. We have to do a little bit more setup for it than that though. So let's compile this again and go back to our level for a second. Let's put in a coin just as an example for right now, and opening up our level blueprint, create a reference to that coin. Because now that we have this specific reference, we can just like type in, I think I called it coin pickup. We can assign coin picked up, or we can bind to it, which is the same thing. So if we assign it, it automatically creates a new event for us as well. So let's say we call this event first coin picked up. We want to move this over to begin play because we want to bind this as soon as the game starts. And now anything we put into this custom event that we have over here, this code will run whenever this first coin gets picked up. Every other coin in the level it's not going to run for. It's only going to run for that specific coin because that specific coin is going to call out into the ether and just say, hey, I've been picked up. And this event is specifically listening to this coin. So let's do something like get the player character here, and we can cast that to BP third person character, and we can jump. That's just a function that exists on the third person character. So now when we run into this first coin, our character will automatically jump. But when we run into any other coin in the level, so let's just duplicate this, we won't jump. So let's play from here to skip our cutscene trigger box. If we run into the second coin, it'll just get picked up. But if we run into this one, it'll get picked up and make us jump. That might not seem too useful right now, but let's think about this for a second. Let's say we have an enemy that is guarding a door to the final boss fight. Something like that, right? Every actor, as we've discussed, has an event already for being destroyed. So what we can do is we can select any actor and create a reference to it. And instead of using our own event call, we can simply say bind on destroyed. And we get another one of these nodes, and we will have to make our own custom event. So let's do that as well. Add a custom event, and let's call that open door, just for the sake of this example, right? We tried to connect these two things up, but it doesn't work. And that is because ondestroyed needs you to also have an input for your event. So if you come over here to the right hand side, we can create an input, and that would be something like the destroyed actor, and that will be a actor object reference. And now those should be able to connect up. That is the reason, by the way, that it's usually easier to use a sign, because it will automatically make a custom event which has all of the parameters that it needs, all of the inputs. But as you could see before, we have a bunch of other events as well. So we also have an on take any damage, take point damage or radial damage. That's to do with Unreal's built-in damage system, which we might talk about at some point in the future. And of course we have the actor begin and end overlap, or when it gets hit by a collision. Those are all event dispatchers that you can assign to with other actors. So if we, for instance, want to have on take any damage, if we have a boss fight that needs to spawn particles when it gets hit, we can put those particle emitters in the world and just assign them to on take any damage for that boss fight. And then that boss fight doesn't need to have any knowledge or any references to those particle systems. But those particle systems can just listen in to when that boss fight tells them to fire. And that is the really powerful thing here, is that it's a one-way communication. And usually you would think one-way communication, that's just going to go horribly, horribly wrong. But the thing is, the sender of this message, the sender of the event dispatcher, doesn't need to know anything about the receivers. So it doesn't need to be dependent on them either. When those change or when those get removed, the sender of the message does not care. And that will prevent a lot of crashing of your game. Not having to intermingle things so tightly together that things are now dependent on each other. I'll take you into the blockout for a level in my own game that we have over here, and open up the level blueprint just to show you a implementation of it that I am using myself, outside of the context of this is just a tutorial. So over here we have a enemy that I'm using for the combat tutorial of my game, and we have a sequence player here that opens up this little bridge over here. And I only want this to open up whenever this enemy has been defeated, because I want to know that the player has a good enough feel for what the combat inputs are to defeat this enemy before they can move on altogether. So what we have in the level blueprints is on begin play, I get a reference to that specific enemy, which is called a BP, basic demon, and I get its undestroyed event, and I bind my own custom event to that, which first plays that specific bridge opening animation that we saw in the beginning. And then also I have something called a blocking volume here, which is this little square over here. And all that is just some solid collision that doesn't allow the player to move through it. Because otherwise, of course, they would fall down into this hole if they try to move over it. So that also gets destroyed whenever this enemy gets destroyed. So let's remove this first coin that makes us jump and do something a little bit more interesting with this second coin over here, using the event dispatches. Opening the level blueprint, let's remove all the event dispatcher stuff that we had before, create a reference to BP coin 2, and assign on destroy. And we're going to spawn in a new coin when that happens. So we get the spawn actor from class node, and we use the BP coin class to spawn in. Then the spawn transform is going to be, we're going to split that up actually. The transform location, rotation, and scale are going to be separately set. And here we get the destroyed actors transform. So we get the transform. And this is why the event that you link to the event dispatcher needs to have a matching set of inputs, because this event dispatcher is also passing through, hey, this destroyed actor is this specific actor that called out. And that can be a number of different input parameters. That can be floats or bools or ints or any of the ones that we've talked about before. Let's split that structure up in. The rotation and the scale can be the same. But for the location, we're going to add to that. And we're going to split the structure pin for the X, Y, and Z. The Z we're going to add nothing to, but we're going to add something to the X and Y. So have it spawn in a slightly random location. So let's get a float in range, a random float. And let's say it spawns between -200 and +200 away in both the X and Y directions. Now, if we compile and we play from here and we pick up this coin, we can see it spawns in a new coin. And when we pick that up, it doesn't spawn in a new coin. Because again, that event dispatcher is specifically talking about this coin. So any coins that spawn in after this one aren't going to have that same functionality, unless we program something that allows for that. How do we deal with that? Well, that's actually remarkably easy, because as you can see, the spawn actor node here has a return value of a BP coin object, which is an actor. So this one has a bind on destroyed on it as well. And you'll probably be able to tell that we can bind multiple event dispatchers on the same event here. And now, whenever this new coin gets spawned, it will immediately bind the event that spawns the next one to the undestroyed dispatcher. And that then allows us to have a infinite amount of new spawning coins, which at the moment I can't reach this one. So a little extra sophistication in the system probably wouldn't hurt. In this specific case though, you do want to worry about the fact that you can see here I changed this from -200 to +200 to using 500 instead. If I just use like between 5 and 6 for instance, so that always spawns in more or less the same location, you will note that it doesn't spawn a next one and it throws an error. So there is a little bit of iffiness that comes with it spawning right on top of the player in this case, which is slightly annoying. For now, the easiest way to deal with that is number one, making sure that these numbers are high enough, and number two, in the spawn BP coin node, putting the collision handling override to try to adjust location, don't spawn if still colliding, or but always spawn. One or the other, doesn't really matter. This will try to make sure that it doesn't overlap with anything when it's spawning. And now we have a coin that infinitely spawns wherever. It does seem to be on a bit of a diagonal, which is weird. That makes sense because there's only ever one float getting generated for both the X and the Y, which is less than amazing. So we want to generate 2 different ones for those, and now it should spawn randomly in some location. Of course, we're probably going to want to go into brush editing here and make this entire platform a fair bit bigger in order to accommodate this randomly spawning coin. And also, I can now walk around the cutscene trigger, which is quite nice indeed. So now we have a chain of endlessly randomly spawning coins until it overlaps with the player, at which point it does throw an error. We're just going to kind of ignore that for now. I want to reiterate though, the brilliant thing about this is any other coins that we put in will not be part of this chain and will not have that same functionality here unless we also in begin play bind it to this event. So we'll see that all these coins, when I pick them up, they don't spawn any new ones because they have not been bound to that event. Then when I pick up this one will actually spawn in new coins when they get picked up. I hope that gets a decent idea across as to how event dispatchers work and how you can use them. I have some more examples maybe to show later. I've got one example in my own game that has to do with UI though, which we haven't talked about that yet, so don't really want to show that yet, but maybe when we get to that UI bit, I'll show you the event dispatcher setup in my own game that I'm using in my UI as well. If you don't quite fully understand everything that we've talked about here today, don't worry about it. It can be a very confusing topic. Just move forward, keep learning, and eventually things will click. And you can always come back to this video after you've learned a little bit more to maybe grasp this entire topic just a little bit deeper and really get familiar with it. I think we've done quite a lot of programming heavy stuff over the past few parts of this series though, so I think next time it's time for something a little fun and a little bit more different, and we're going to talk about setting up some fun and interesting lighting for our level here. So I'll gladly see you all back when we do that. Alright, we've done a lot of programming stuff, we've done a little bit of sequence animation, but now let's do something a little bit more artistic, and that being lighting and a little bit of post-processing involved with that as well. A lot of color related work. But before we do any lighting, there's one thing that I would recommend you do, and that is come into your project settings. If you don't have a tab for it, you can go to Edit and then Project Settings. And in that we'll look for Auto Exposure and turn that off. Because otherwise, your camera will always automatically try to compensate for a space being either dark or light. And that gives you a harder time to work with lighting up an area to the point where you actually have it the way you want it to look like. Because if you want something to be a little bit more dark and mysterious, the auto exposure will likely mess that up quite a bit. So turning it off, you can immediately see things in this box. I did a little bit of level design stuff off screen to make this work a little bit better. It's a little darker. When we go out here, we can see immediately it's a lot lighter. This looks a lot more pleasant, at least to me. So what we're going to do is we're going to go through some of the lighting and then the post-processing. So first and foremost, let's go through some lights. I have a short video that explains what all these different lights do, so I'm going to go through them real quick. The directional light, we already have one. That is more or less a sunlight. That's a light that casts light from the same direction over your entire level. So no matter how far you walk in a certain direction, the shadows will always fall in the same direction. So you can see the shadows always fall, in this case, from that direction to here. If I go into my directional light, I can change its rotation to change how those shadows fall. And it works like any other object. We can change the rotation however we want. In this case, it's also linked to the skybox dynamically to make it match with the time of day that an angle like that would give. So that's mostly to do with the Y rotation. And actually, I think I quite like the idea of having, let's see, the sun is over there now. maybe having the sun coming all the way from somewhere over here. I quite like that idea. So that makes things even a little more dark in here. Gives us even more reason to be lighting it up manually. So then we make our way out here and we get to this like sunset type deal as far as looks go, which I quite like. I'm going to lower the intensity to 5 though, to make it a little bit darker. And then we'll move on to some of the other things that we already have in our scene. One of them is the exponential height fog, which you can actually see quite well here what that does. If I turn it off, you will see that a lot of the light scattering, the slight amount of rays that we have here, you can see it a little bit better through this object, disappear, as well as the entire bottom part of our world. That entire thing is colored just through scattering of light. If you want that to be a little bit more accurate, you can enable volumetric fog, which makes that more physically accurate, but this is very much more computing intensive to run. So if this looks good enough to you, you should stick with that. The sky atmosphere is the air itself, so if we turn that off, you can see everything goes black as well. These two things together kind of make the basic setup of any world that you have. The skylight takes in either a cube map, or in this case is real-time captured, and uses the skybox to cast light onto your scene. So if we turn that off, you can see the little bit of light that our skybox generates disappears, and this is generally good for creating a baseline brightness in your scene. So if you want nothing to be absolutely pitch black, that's kind of what a skylight is generally good for, because it doesn't cast shadows usually. And then volumetric clouds aren't really light related, but of course that's those clouds that we see. So those are the things that I'm not going to be adding on my own. That's what these template maps come with by default. Going back inside, I think it's time to go through some of the lighting options that we have. That being the point light. As you can see, it emits a light from a point. And here we go through some of the options as well. So we have the intensity. I think that's pretty straightforward. That's just how intense the light that it emits is. The light color, you can make it literally any color that you want. Let's just keep this one on green. Now, next, the attenuation radius is how far the fall off of the light reaches. You might think, why is this not just infinite? And as soon as an object is too far away, it shouldn't be lit by the thing just based on the intensity anymore, right? And if you're working on something like Blender, that is very much the case. But we're trying to work with something that is real time here. And as such, we, specifically with lighting, need to be cognizant of the fact that lighting can be a pretty heavy operation to compute. So the less your radius is for affecting things around you, the cheaper it will be to compute. So keep this as small as is possible for any given light. Sometimes it does need to be huge, don't get me wrong. But if it doesn't need to be huge, you don't want it to be huge. We can also use a color temperature, which just makes it a warmer or a colder color. And if you don't exactly know what that means, warmer colors are more orange, colder colors are more blue. That's a thing in cinematography, because if you are using artificial lights, oftentimes those are warmer, and cameras, and in this case, your game engine, will need to know how to deal with that, while sunlight usually ends up being, maybe a little counterintuitively, colder, more blue. And you can test this out yourself if you have a camera where you can set the white balance to something manual, set it to something where it looks good inside your house, and then take it outside. You'll see the pictures you take with it are really, really blue. And that's aside from the actual color of the light. So that influences the color that you choose the light to emit. It's an option that you can use. I generally just stick with light color because we don't need to get too technical about the cinematography here. You can turn off Effect World. Don't know why you would do this, but it's certainly an option. Something more useful though is turning off casting shadows, because of all things, casting shadows is one of the most computing intensive things of calculating lights, because just calculating, okay, what is in this radius and we'll add a certain value to these textures is not that intensive. It's the calculating of the shape of the objects in the way and how they cast shadows, that actually gets very intensive. So again, if you want to optimize your lighting and you have a light that doesn't need to cast shadows, turn this off. And then we have the volumetric scattering and indirect lighting intensity. Indirect lighting intensity is just how much you light things up through bounce light, I believe. And then you have volumetric scattering intensity, and that is coming back to, if we go into the exponential height fog, what I showed you before, the volumetric fog option. If you turn that on, and I will put this in a little bit of a more normal color and turn down the intensity a little bit as well, you can see there's a little dot over here, and that is because this light is scattering through the fog. So if we increase that scattering intensity, you can see that that little foggy dot that we have here becomes more obvious, especially against a darker background. And then if you want that effect to be even stronger, you can also increase the effect from the volumetric fogs side, I'm pretty sure, through the scattering distribution. So now we have this very, very obvious, like almost lens flare looking thing. But that's not what we're doing here today. So the moment I turn off volumetric fog, that entire setting literally does nothing. And all the other options that we have here aren't too relevant for right now. You can say the maximum draw distance. If you are a certain distance away from it, it should stop emitting light. Again, it's a performance thing. All that kind of stuff. We have light functions and light profiles and stuff. We're not going to talk about any of that right now, today. So the different types of light, let's talk about that for a moment. We have this point light. Then we have a spotlight, which does exactly what you imagine it to do. Instead of casting light in all directions, it casts light in the direction that it's facing. So if we go to the point light, we can rotate this thing around, but it literally does nothing, of course, because it's casting light in all directions. If we rotate this thing around, however, you can see that it's definitely doing things. We're going to go back to -90 though, because it shows some of the other things that I want to show off a little bit better. We have the attenuation radius, but here we have some other options as well, that being the inner cone and the outer cone. The distance between where the inner cone ends and where the outer cone ends is the fall off distance of the light. So the light will be at its most intense all throughout where the inner cone shines. And I'll go a little bit closer so that you can see the different lines. Those blue lines, those darker blue lines are the inner cone. And the outer blue lines, the lighter ones, are the outer cone. So if I make those really close, you can see that the fall off here becomes very sharp and it's a very obvious circle. The inner cone is very small and the outer cone is very light. The fall off is very gradual and it's a very soft light. In much the same way, we also have rectangular lights, which don't cast in a cone. Let's also put that at -90 degrees so that it's facing the ground here. But instead, they cast light in a square. And here we have the width and the height of that square, or rectangle in this case. And this can be really nice to light up things like an entire hallway with just one light. Because just calculating this one light in this shape is a lot better than putting in a lot of point lights to light up a similar area. And you can tell that this is a pretty soft kind of light. So even if we increase the intensity, the fall off of it by default is really, really soft. There we have the barn door angle. It's set to 90 degrees. So that's kind of like the fall off of this type of light. But if we all the way get that back to 0, you can see that these barn doors, as they're called, are now pointing straight downwards. I'll show you from this angle again how they move. And the longer they are, the more focused this light becomes as well. So now you can definitely see what this does. Just like that, we are focusing the light in a much more rectangular shape. And now we have a more rectangular shape of light. So those are the 3 types of main lights. They're rectangular lights, they are point lights, and they are spotlights. Point lights being the most computing intensive usually, the other two being, I believe, pretty similar in their intensity. But point lights, also the easiest to just place around and have fun with. So let's do some of that. We'll put in a rectangular light in our starting area over here. So we'll put that at -90. We'll pull that up a fair bit and then just make this source about the size of our starting area. The barn door length will go up a little bit and we'll try to focus it down a little bit more, increase the intensity. And we can just play around with things a little bit like this. Maybe we want to focus it down even a little bit more. That's a pretty good start. And then let's use this point light as a base. I want to make this a little bit more bluish, purplish for just like atmosphere reasons, right? Decrease maybe the intensity ever so slightly and start placing some of these around our walls. Now, there's one thing that you should note because we have 3 types of lighting, and I'll explain those to you in a moment once I have a couple more lights set up here, because you'll be able to see what they actually do and how differently they function. Now, everything we have at the moment is set to a stationary light. Is that true for the rectangular light as well? It's also set to stationary. So there's a couple of different ways you can deal with lighting in a game engine. Static lights get baked down, which means that they actually don't get rendered as lights at all. They just get baked down into textures that the engine then overlays on top of the actual textures of all of the models in the scene. So it gets calculated once before the game is even compiled and built and sent out to the players. And then on the player's end, it doesn't need to calculate anything ever again. It's really fast for rendering. So static lighting we generally use for lighting that is only really meant for the environment itself. Because as soon as even something like a player walks under a static light, that player is not a static element. And as such, it won't have that light baked onto it. So that's generally what we use that for. Things are light that's just supposed to light the environment in a static way. Next up we have stationary. Most of your lights will be stationary, usually. That's why it is the default option. This is kind of a mix between static, which is entirely baked, and a movable light, which is entirely dynamic, calculated in real time. If there is something that this can bake onto, a static mesh, which is static, something that doesn't move, it will use that baked lighting. If there is something that moves around, like the player or like these blocks over here, it will see, oh, wait a second, this is not a static object, so I will not use the baked lighting for it, I will use the real-time lighting for it. So it's a very intelligent kind of light. Since it still partly relies on being able to use static baked light, you can't move the light source itself. Which is why the last one is called movable and not something like dynamic. Because this is totally dynamic and is able to be moved around as the light source itself. So if you've got something like a disco light or whatever, something like that, a spotlight that's like searching through an area and you want it to be an actual light, you would set that to movable. You do want to be careful with having too many movable lights in one scene because it will tank your frame rate really, really quickly. Again, most of the things that we want to use are stationary because generally we want to bake where it's possible for faster rendering, but most lights you still want to be able to influence at least the player, right? And the player is not a static object. So let's play through this and just see what this looks like right now. We can see if we go up in the corner here, it's all dark, and then in the light here, it's a little bit lighter, and we've got this cutscene, which looks a lot better now with a little bit of lighting applied, and now we have our sunset at the outside, and it's all just kinda neat and nifty. So let's just die, I suppose. And when we get up here, we can see when we get to the purplish lights, that casts very nice light on the player itself when we get close to it. And we might need to have another rectangular light here, rotate that down to the floor, and maybe just for a little bit of fill lighting, and let's make this like ever so slightly green, maybe. Also slightly green seems about right. That seems fun. And you will note that the intensity is the total intensity of the light. So if the light source, in this case the rectangle, becomes bigger, the light gets more spread out, and to get the same brightness out of your light, you need to increase the intensity. And I also need to increase the radius for this specific one. And now we have a nice little mix here, and we can see there's a lot of shadows going on from all of the lights, and we've got this green light and we've got these purple little highlights everywhere, and it is starting to look a lot more fancy than it was before. Now, I can talk about this all day, and you can tell I am a little bit more long-winded than I was before, because this is a more artistic kind of thing, and it's harder to explain all the proper uses of this. And I was planning on including post-processing in this video as well, but I'm looking at my recording, and it's already long enough as it is. So we're going to go into post-processing in the next video. I'll explain what post-processing does, how you can use it, and how powerful it is, because you can make your entirely own custom post-processing materials, which is really exciting. For now though, thank you for watching. I hope it was helpful. This is the basics of lighting in Unreal Engine, and whenever we get around to adding post-processing and adding a couple of materials to this stuff, this is going to start looking really, really cool. Our level is starting to look like something that might actually look halfway decent now that we've added a couple of fancy lights to it, even though I threw them in kind of willy-nilly. But there's one thing that we still definitely need to talk about as far as the looks and the artistic vision of your game goes, and that is adding post-processing, because you can't just do things with lighting. Sometimes you need to add in a post-process volume. As long as you're inside of this volume over here with your player, the game will render in whatever way you specify in all the myriad of options you have here on the right hand side. So for now, we're going to just show you that through increasing the global gamma. And let's make it a little bit bigger so it's easier for me to walk into. And then when I play from here, you can see everything is normal. The moment I walk into it, you can see our post-processing effect takes place. It's important to note that it's not your character's position, but it's the position of the camera rendering your current view that needs to overlap with the post-processing volume for it to work. So that's also a reason why I want things to be a little bit bigger usually. So let's make a post-processing volume that encompasses this entire inside until we go to the outside. So we have a different look on the inside and the outside, and then we'll work on what it actually needs to look like, because the way it looks like right now, it's just not that good. And we should be able to do that in brush editing mode, because the post-processing volume is just a brush. So the way we can do that is just select that, and theory, maybe the brush even gets cut up. I don't think it gets cut up by any subtractive brushes actually. That's good, that's very good. We wouldn't want that. Let's make it a little bit bigger than the box itself, and actually not in this direction, because here I really wanted to, as soon as we go outside, start showing the way I want it to look like outside. Well, now this thing is big enough to show in the entire inside here. Let's go over all of the options after I have reset my gamma, because I don't want the gamma to look like this. There's no way I'm going to show you literally every option in here, because that's going to take way too goddamn long, but we can start with a couple of often used things, like this mobile depth of field. I'm not going to talk about. But bloom is, well, the amount of blooming that highlighted areas have. So we can see here, for instance, this has quite a bit of brightness on it. Let's increase the intensity for the bloom, and you can see there's a little bit of a glowiness effect to it, which we'll have seen in quite a few games. And you can set the threshold as to what parts of your image will need to bloom and what parts won't need to bloom. Personally, I want to warn you, it's very easy to overdo it with the bloom, and just adding a lot of bloom doesn't make your game look good. You might think that it does at first, you're going to regret doing that later. Don't overdo it. Do add some, because having none at all also looks weird and unnatural, but don't add too much. So the intensity being at 8 is less than optimal. Yeah, I'll extend this down, and just show you what it looks like when the bloom is turned down versus turned up. That's the effect that bloom has. And you can see turning it entirely off doesn't look that good, but just setting it to 1 is usually really all you need. Just having a little bit of bloom, because that is how cameras work. And for inside, I'll do a little bit more. We've got a bunch of advanced options, which I'm not going to talk about. Now, going through a couple of things real fast is chromatic aberration. I'll show you through turning up the intensity. It's the discoloration in a vignette effect. So at the corners of your screen, the discoloration between the red, green and blue channel being separated from each other is going to be more intense, while the center of the screen doesn't have it as bad. And we have a start offset to say I only wanted to affect the very edges of the screen, for instance, or literally everything. Usually not an effect that you throw on things too often, I'll admit, but it's a cool effect to add in certain situations. We can add a dirt mask, and I don't know if we have any dirt textures with the engine by default. It doesn't look like we do, which makes this kind of hard to show off. But we can try to do it while looking into the sun. So when you're looking at something bright, the dirt mask is going to be kind of an overlay in the very bright hotspots. So if we turn up the intensity here and you look at this spot over here, you'll start seeing the texture that I put in. In this case, that's a little bit of a weird texture because, of course, it's a brick wall. And I don't think I have any... Do I have just a noise texture, maybe? Purple noise. Well, that feels a little bit better already. So we can use that to just make things feel a little more imperfect. That is the name of the game. Making something look good is getting rid of perfection. Which sounds really weird, I know. But things aren't perfect in the real world. If you want to make things look realistic, you're going to need to add imperfections. Because most of the things you make through processes or digitally are going to be too perfect. We have some camera settings here, which I'm not going to touch at the moment because they are not all that relevant, to be honest with you. Same with your local exposure. If you're interested in this kind of stuff, it's more cinematography related and it's very good stuff to know. But I'm trying to keep this a little bit compact, and these aren't the most important. We have lens flare options. Fucking always love having a good lens flare. It's pretty self-explanatory. These just generate dynamic lens flares when you look at a bright source of light. So we have an intensity slider, of course, as always. How intense are they? We have the tint. If we want to give them a certain color within this post-processing volume, we can do that. So let's make all the lens flares within here like a pinkish color. I like that. The bokeh size is pretty much just how blurry or how big, you could say, the lens flare is. So in this case, that would be insane lens flares, which we might even be able to see from the inside. No. But that is where the threshold comes in. The threshold is how light something needs to be in order to generate a lens flare. So here we have this, and if we put this up way too high, well, the sun is just too bright to cut out altogether, it seems. But if we turn it down instead, we can start seeing other things casting lens flares as well. In this case, I think it's the reflection on this white block that's casting one. Easier to see if we turn down the bokeh. And now we can see there's quite a few things here casting lens flares into our player. So we want to increase the bokeh for that a little bit and probably increase the threshold again. And now we have some more subtle lens flares that we can maybe work with a little bit better. And again, we can put in textures for the bokeh shape, but I think that's pretty self-explanatory as well. We have some vignetting options. So if we want to have a vignette here, which actually inside here in our little dungeon area, for lack of a better term, it's probably a good idea to have. Next up, we have the depth of field, something that a lot of games these days really also like to overdo, but it can make things look a lot better. So a lot of this stuff is pretty technical, so I'm just going to go over them real quick. The sensor width is more or less just how out of focus your background will be. The squeeze factor is how squeezed the blur in the background will look. And then we have your focal distance, which is the part of your scene that is actually in focus. And this is a bit of a trial and error thing. You want to have your player in focus, of course, and everything else being slightly out of focus. And this whole depth of field thing can give very interesting impressions because, as you can see, through everything being so out of focus in both the foreground and background, it makes my character feel smaller, because usually this shallow of a focus, meaning that there's very little that's actually sharp in focus, is usually only done in cinematography with actual cameras with macro photography or macro filming, meaning you're filming something up really, really, really close. Emulating that shallow depth of field can result, if you have a wide shot like this is, in it feeling like you have a much smaller space. And if you're making something like a Toy Story game, for instance, would be a very good use of a technique like this. Let's set the sensor width to something slightly more reasonable. And if we want to come back up here to the camera settings, if we change the aperture, that also messes with the depth of field in a much better way. So if we set this to 1, our depth of field becomes more shallow, but in a much more realistic, believable way. So as you can see, now we're still fairly small compared to the environment, of course, but we don't feel as miniature. And finally, we get to the color grading stage, which is, funnily enough, probably one of the more important stages here. We can change the temperature that we use, either color temperature or white balance. And just as I talked, I think in the lighting video, we can change the color balance here. This goes the other way. This is kind of like color compensation. So that's because we've got it set to white balance. If we set it to color temperature, we have low values being more orange and red, higher values being more blue. And then the tint goes from green to magenta. So we can do some really wacky shit with that. Of course, if you want to color things and not use this, we also have these color wheels over here. So we can set the saturation, which just makes things look more saturated. I think 1, maybe 1.2 is pretty good for this. We've got the contrast, which makes brighter things brighter, darker things darker. We can actually maybe even lower that a little bit for this area. The gamma is just the overall brightness of your whole image. So you can, for instance, increase the gamma and contrast together. And if we then turn off the post-processing altogether, you can see it gives the entire image a bit of a boost without feeling too washed out. The gain does something similar to the gamma. It's a very technical explanation as to what the difference between the two of them is, so I'm not going to go into it too much right now. And the offset, once again, does something that is also very similar, but in a much more ugly way, so we're not going to use it. Then we have those same options for the shadows, the midtones, and the highlights. The shadows are the dark parts of your image, which the cutoff you can influence by this shadow max. So if we put the offset here to 1, just to show you, it will only offset things it considers shadow all the way up. And if we decrease what it considers shadow, now we get this weird looking thing. And if we increase what it considers looking at when it looks at the shadows, it does all that. So you can use this as a more accurate way to, for instance, if we want to increase the gamma on the shadows, that will just make the shadowy part of our scene a little bit lighter. And then if we increase the contrast in the shadows again, it's doing the same operation as it did before on the whole image, but it's taking the brightest shadows and the darkest shadows and doing the operation on that instead of the brightest parts of the whole image and the darkest parts of the whole image, meaning that it's better at preserving detail when you do it specifically on the shadows. Then you'll see the midtones doesn't have one of these max sliders where the highlights do. The midtones is literally just anything that is above a shadow and not yet considered a highlight. And the highlights, of course, are the brightest parts of your image. Now we've got a bunch of global illumination stuff, which we're also not going to be touching right now. And everything else is pretty secondary for the time being. I've already given you much overload in information. I want to talk about one last thing though, and that is the possibility to add your own post-processing materials. You can add your own materials that you can design to have your own specific post-processing effects. We'll walk through this post-processing and see the change from jumping from the inside to the outside, while where we won't have the post-processing any longer. And then I'll show you in my own project one of the post-processing materials that I have created to show you the capabilities that you have at your fingertips here. So first and foremost, this is no post-processing. You can see we don't have the lens flares and stuff because I was dumb and didn't extend the post-processing volume far enough. Then this does have the post-processing on it because these cameras, well, this one not, but that first camera is inside the post-processing volume. And you'll see when I walk forward here, suddenly we have the lens flares and everything else like that, and everything is a little bit brighter because we are now in the post-processing volume. And we can jump onto this, and we get a look that we just created, which admittedly is a little overdone, but you kind of get the point, right? So then we jump out of here, and we can immediately see our post-processing is gone again. There's one way to fix that. If you want to make a post-processing volume that just encapsulates the entire world, we can look up boundless, unbounded, infinite extent, whatever you want to call it. If you tick that, no matter where you are in the world, you're going to have this post-processing effect enabled. So we're outside the volume now, but we still have the lens flares and all that good stuff. So if we play from here, we'll probably be, very bloomy because we have direct sunlight on this very reflective looking character. So this is what I mean with you can overdo it with the bloom. Don't overdo it with the bloom. So here in one of the rooms of my own game that has a little bit of level design already put into it, I have this post-processing volume that creates all of these little lines around the outsides of objects and where the normal maps, which we haven't talked about what normal maps are yet, but don't worry about that, create. So we can look into this, and then if we go into my post-processing materials, we can see my line shader. I have it set to very low at the moment, but we can set it to much higher. It creates these black outlines around geometry, and that can be real nice. So if we turn that off, that's how big of a difference it can make. The grass, it looks a little bit messy. I will be ready to admit I'm still working on seeing what exactly I want to do with the grass, whether or not I want to exclude that from the post-processing. I probably will end up doing that. But we can just look at this, and it is a material which has a parent material, and that parent material has a metric ton of different nodes, which actually, it's not all that bad. I do have a full tutorial on making this specific post-processing material, together with a couple of other ones, to create a pixel art look for your 3D game, already on the channel. So if I don't forget, I'll try to leave them below in the description. But this post-processing, it's good for color grading and all kinds of visual effects like the chromatic aberration or vignetting. This is where the real power comes in. Programming in your own materials which do things that you want them to do. The possibilities are quite literally pretty much endless. So now we've looked at a little bit of more artistic input to create your games, and next time I think we will keep going with that because our level still has this material on literally everything. I think it's time we start talking about applying some materials and making some materials of our own to make things actually start looking good. We've got some level design here, and we've got lighting, and we've got post-processing, but still we're using this checkerboard pattern. So today let's take a look at the basics of materials in Unreal Engine. One of the big upsides of using Unreal Engine is that you can actually use a lot of high quality pre-made materials. So if we come up here into Window, we can open Quixel Bridge, which is a kind of gigantic library full of 3D assets, so models as well, but also a lot of materials that we can use. So you can see here, there's models, there's plants, and there's a bunch of materials. Today we're going to be looking into the materials. So if we look into surfaces here, we can see a bunch of different categories as to what kind of surface we want. Let's go for a stone surface here today. And here I chose a castle stone. So we can say we want the castle wall, and then we can choose whether or not we want low, high, highest or medium quality. Usually medium quality is good enough. You should be aware of using high quality and highest quality assets really starts eating up a lot of video memory, which is usually a big bottlenecking point for your graphics. And once you're signed in, which you can do with your Epic Games account or whatever other type of account you want, you can download this asset, for instance. And let's also, because this is a wall, we can't use a wall on everything, so let's also use this castle cobblestone, and that we will use for the flooring. It also gives you a bunch of related assets and even the collection that this comes in. So if you want to make a castle ruin, there's an entire collection for that which we can download and have a bunch of assets to work with. Especially for things like prototyping or a game jam game, things like that. This is fantastic. Once you have those downloaded, it will show up here in your local folder under Mega Scans. And you can see I already have a bunch of assets here from previous projects and videos, which I have stored locally. And once the two materials that I'm downloading are done downloading, they will show up here as well. And I'll be back with you in a second. So the castle cobblestone is finished downloading now. And once we have that, we can select it through our local folder here. And then we can add it to our project, where it'll just make a new folder, Megascans, services, and then one specifically for this material. And that will create a material asset that we can use in a moment. And now it's as simple as just drag and dropping your material onto whatever surface you need that material on. And you'll see that with these box brushes that we've been using, we can actually do this on a per face basis. If you do this on a full static mesh, which sometimes with entire actors, it's a little iffy on that. So we can go into the cube static mesh components here. If we go into all, we can then see the material that this is using. We can always just drag and drop that into there as well. If we just lower this a little bit, we can drag and drop it into there. And you'll see it actually does the entire model. So the way we can do it on a per phase basis is very much just something we can do for these box brushes, which is part of what makes them so fantastic. So if we select our faces here on our box brush and come into the details panel under the brush component, we can see surface options here. And there we have the UV scale. And long story short, this is just the scale of the texture on your object. So we can see that if we change this to 2 and we turn on this lock so that it's always proportional, when we apply, the texture becomes bigger. If we want it to be smaller, we can set it to something like 0.5 instead, and now the tiling becomes smaller instead. I think something like 2.25 probably would be pretty good for what we're going for here. And we can do the same about all that on all these faces. So here again, we can also go into our UV scale, let's say 2.5 for both of those as well. Do make sure that these are the same number. And then we can use this cobblestone wall for all these other faces around here as well. And then naturally, the tiling here is way too small as well. So let's actually set this up to a bigger number, something like 3 right away, because that's going to be pretty necessary. Well, it ain't perfect, but it is already looking a hell of a lot better. And to be fair, this box brush method that we've been using, usually you would only use this to block out your levels. You wouldn't often really start to apply the actual materials to this. Usually you want to replace this with your own static meshes that you have made in Blender or Maya or whatever. So for now, this is still looking pretty flat and not finished, and that is because it is. Anyway, this is a really good way to quickly put some graphics on your levels, but you're going to want to do something more than that, right? You're going to want to make your own, and that can be very complex in a lot of ways. So we're going to go over the most important things to understand and how to set up your own materials. So going back into our content folder here real quick, we can just simply right click and make a new material, and we'll call this something like test material, which is a very bad naming convention. You probably should prefix this with something like mat and then the name of the material itself. That gets us this interface, and there's a lot of things to talk about here. So we've got our details panel here where we can choose a material domain, a surface, a decal, a light function, a volume, post-process, or a user interface. We're going to stick with surface materials for now, so don't worry about the domain. The blend mode is a little bit more important, most of your materials, where possible, are going to be opaque, meaning that you're not going to be able to see through them at all. This is the cheapest for rendering. We also have masked and translucent, and the other ones I'm going to skip over for now. These are the three you're going to be using the most. So what's the difference here? Opaque, you can't have holes in your material at all. So anywhere where there is geometry on your 3D model, there's going to have to be something to see. Whereas if you go into translucent, you will note that there is a fair few things that go blank here, like the metallic, the specular, the roughness, all that kind of stuff. But instead, we do get an opacity. And I'm just going to add a quick value here. And we can see that if we set the opacity to 0, this thing disappears. But if we set the opacity to 0.5, we get a see-through material. Now, that's really cool because we can now make materials that are see-through. So things like glass are now suddenly possible. And oftentimes you'll want a water shader to also be somewhat see-through, that kind of thing. That's where translucent materials really come in handy. They are pretty expensive to compute for your GPU though, comparatively speaking. So only use translucency where needed. And that is where masked materials come in. You'll see that the opacity is no longer available when we go to masked, but instead we get the opacity mask. And this is not a you can see through it kind of deal. What you can do with an opacity mask is just say these parts of the image you can see, and these parts of the image you cannot see. So if I plug the 0.5 into here, that'll do nothing, because it won't disappear unless it's actually set to 0, at which point you will note that it has some trouble with like the shadows and stuff like that. We're not going to worry about that too much right now, but this is a cheaper way of creating holes and see-throughness in your materials. So let's just real quick, I'm going to add a noise into here, into the opacity mask, and you will see that we now have holes poking through here. And if we, don't worry if you don't understand what's going on here, but if we add some texture coordinates and we do some other good stuff here to make this all work, we can now make this noise pattern a little bit more manageable for us. So let's say we want to have this at scale 50. Is that a little too much? That actually kind of works. So now we have this material where we have a noise pattern where some parts of the noise make the material visible and other parts make it see-through. Again, don't worry about the whole texture coordinates and noise node and the multiplication and this appending and all that kind of stuff. We're going to get into that at some other point. Matter of fact, the whole material stuff is complicated enough to the point where it could have a series in and of itself, which I probably will do, because otherwise this would go on for way too long in a course that is supposed to just cover the basics. So let's go back over all these different inputs, at least the inputs that are the most important. And we're going to go back to a opaque material, because most of your materials are going to be that opaque. We're going to talk about the base color, the metallicness, the specularity, the roughness, the emissive color, and the normals here. Everything else is a much more niche use case, which we're not going to get into right now. So the base color is exactly what it sounds like. It's a color. So if I hold the 3 key on my keyboard and I click anywhere, that gets me a vector 3 value, which is literally just a color, right? So I can just say the color here should be this pink. And if I plug that into the base color, we'll now see that our material is a pink color. And I think what we should do, because we have these coins in our game, which don't really have too much going for them as far as material go right now, I think what we should do is we should make a material for that coin. So let's make it gold, which we can do by making this thing a yellow color. But this still doesn't look very gold, does it? And that is where our second value here comes in, the metallic value. This is literally a value that just makes things look metallic. Don't ask me what it actually does mathematically speaking, because I don't know. Just when this is 0, it's non-metallic. When this is 1, it's very metallic. You can give it a value in between 0 and 1 if you really want to. Generally speaking, metallic is a value that you just put at 0 or 1. So if we put 0 in here, you'll see that doesn't change anything because I believe by default the value for this is 0. And then when we set this to 1, we can see this now looks a lot more metallic. It does something with the reflectivity, but in a different way from actual reflectivity, because we're going to get to that in a moment. Oh, by the way, the way you make this little node over here is just holding a 1 and clicking. That's how you can make a scalar node. And in much the same way, we're not going to get use out of that today, but you can also hold down 2 and click, and that gets you a node with just 2 values. Which you might be able to see if you use the top pin out of these nodes, the white one, you get both of the values. So you get a vector 2 or a vector 3 value, much in the same way that we have the positional data in our blueprints. That's a vector 3. It has an X, a Y, and a Z value within one variable. But you can also just use the X value or the Y value, and in the case of the vector 3, the Z value separately. So if we just put in this red pin, you might think, oh, it's going to be red. No, it's not going to be red. It's just going to give you the X value from this vector 3. So we can see that's pretty high up because apparently yellow is pretty close to red, which makes sense because yellow is red and green combined. So if we put in green, we also see that's pretty good. But if we put in blue, we can see that'll be a lot more dark. And it's important to note here, because we're separating these things out, they lose their color value because colors always are a red, a blue, and a green combined together. So these will output grayscale. Anyway, we have a little bit of a golden color here, but we probably want for a coin, we want it to be nice and shiny, look like a freshly minted coin, right? And that is where the roughness comes in. We'll get back to specularity in a moment because that's a lot more technical and generally not something you really want to mess with. And the roughness, again, is just a single value between 0 and 1. And by default, that is set to 0.5, so halfway through. If we plug in 0, we'll see that the roughness makes this thing pretty much look like a mirror, meaning that it's going to be very, very reflective. If we set this all the way up to 1, this thing becomes very non-reflective, at which point that generally doesn't go that well with metallicness. But if you don't have a metallic material, it kind of feels kind of chalky, almost as if it is, well, made of chalk, because chalk disperses light very evenly. It's a very matte kind of material. For this coin, I think we're going to want something like, let's do 0.25. That seems pretty good for this material. Now, we're going to take metallicness out of this for a second because I need to explain specularity to you. Do you see this? I think you can see my cursor. Yes, you can. Do you see this little bright spot up here? That is a specular highlight. And in very technical terms, a specular highlight happens when the reflection of a material reflects directly into your point of view. So we have a light source somewhere around here hitting this spot, and a lot of the reflective light just goes all over the place and we just get the general color. But the rays of light that directly bounce from this surface into our camera, they become these highlighted white spots. And if we set the specularity to 0, you'll see we don't get any of those spots. So the specularity is more or less just a value as to how sensitive your camera will be to that reflectivity. It's not quite how it works, but that's the easiest way to think about it. So if we set this to 1, we'll see that it's a lot more aggressive. And of course we can go somewhere in between, so 0.5, we'll see it's a little bit less aggressive. It's not something that you usually mess with a lot. And now if we combine that with metallicness, we can once again see if we go 1 and if we go 0, the metallicness kind of does something with the specularity as well. So that is, again, generally something that I don't mess with, but something that is important to know about. The next one that is going to be very useful for you to know about is the emissive color. For our golden material, that's not really going to be too relevant, but let's, instead of using the base color here, let's use the emissive color instead. And that gets you a very similar result, other than the fact that suddenly things don't look metallic anymore. And that is because this thing no longer is really receiving light. It's emitting light. So whereas before what we saw was the light of the world interacting with just the surface color of this material. Now this material is actively generating its own surface color, and if you have lumen global illumination enabled, this will also actually emit light into the world. And the really cool thing about emissive colors, and this is very easy to fall down into a rabbit hole of using this to just make things look good, and to a certain extent that does work, but if you multiply this color value before putting it into the emissive color, if this color value goes beyond the value of 1, which you can't do in just picking a color, sadly, but if we just multiply this by something like 10, you will see that it starts to approach looking white, but it's actually glowing around the edges of the, well, in this case, the sphere, whatever model it's on. And this glowing, this blooming is something that for emissive lighting, the engine has built in. And if we take this to its extreme and we do 100, you'll be able to see at this point, it's more or less starting to look like a sun. Then again, we're trying to make a gold coin here, so the emissive color isn't really gonna be that important. But in the next video, we're going to be talking about particles. And if you're making specific materials for particles, more often than not, you're going to use emissive outputs for particle materials. Not always, but generally speaking, that is something that I do, at least. And just for the comparison, if we just put this into the base color, it's just gonna end up being white, because the base color is just kept at pure white. It can't display anything more than just pure white. Then the last important pin here, there's a couple more pins that we could talk about, but the last very important pin here is the normal pin. And this requires a little bit of explanation as to what normals are in the first place. Because if you're new to 3D, you probably don't know what a normal is. And you're like, oh, that's just what it normally should look like. And that's not what that is. A normal is a direction. So let's save this material real quick and go back into this map just so that I can show you through this cube. So we've got this cube here, which has a number of sides. And each of these sides is one polygon. Those polygons all have a direction they are facing. And if you don't do anything weird with your normals, by default, that is perpendicular to the surface of that polygon. So for this top polygon here, its normal is just pointing straight up into the sky. For this polygon over here, its normal is pointing over in that direction. For this one, its normal is pointing over into this direction, perpendicular to its surface. Which is very important when calculating light, because the normal is what decides how a face, a polygon, should be lit. If for some reason your normal is facing the wrong way around, that face will get lit as if it is turned around. So if we turn the normal for this top polygon, instead of going up, to be going down, if we put a light above this face wouldn't get lit. Instead, it would get lit if we put a light below it. And you might be thinking, okay, so why is this relevant information? That's how the lighting of the engine works. That is way too deep for me to even care about understanding how and why that works. But here's the kicker, right? That is done on a geometry level. So if you want to add more detail for light to be able to interact with, you need to add more polygons, which is generally a pretty expensive thing to do as far as your computer goes. Adding more lighting information onto a lower poly model is something that does persist. And that is where normal maps come in. A normal map is a texture, just like any normal texture that you can use, which has information about these normals, so the face direction, on a per pixel basis instead of a per polygon basis, making it much more cheap to store and making it much more cheap to calculate, because you don't actually have to render all those polygons facing in different directions. The engine just needs to know, okay, a light ray hit this pixel and this pixel is aimed in whatever direction. So if you have a normal map, you can put it into this little input over here. And I'll show you one of the materials that we downloaded before You can see this is a different interface. We'll get to that in one moment. But you can see that it has the just regular texture here. It has a place for metalness, ARD, we're not going to talk about that at the moment. And then it has a normal texture. So if we open that up, we can see that we get this really weird blue image. And this is what a normal map looks like. So every single pixel here has information on the red, green, and blue channels, which corresponds to the X, Y, and Z directions in the world. So if we zoom in a little bit, we can see that these pixels over here are a lot more red. So they will be rendering the light hitting it as if these pixels are facing into the positive X direction. Whereas these pixels over here are a lot more green. So they will be rendering as if they are facing in the positive Y direction. Usually the base color of your normal map is this kind of lightish purplish color, which you can just think of as a neutral normal. That is a lot of information and a lot of technical mumbo jumbo. So let's try to make a procedural normal map here for a sec. So if we do all of this stuff here to make our noise into a normal map, we can see that there's all this detail here, which looks like there's just a lot of geometry. But if we zoom right up close into it, we'll be able to see that, in fact, the geometry here still is literally just the same sphere that we had before, and all of the extra added detail that we can see here is actually simply different light interactions with the surface. So if we go into our coin here and put that material on that coin, we'll be able to see that we probably need to change a fair few things about the scale here, but we have all of this detail which is purely coming from the texture and will interact with the light. So if we put this closer to a light, where's the nearest light? There it is. If we put it closer to a light, we'll see that it interacts with that in interesting ways. That said, we're making a coin here, and I don't think particularly that we need to add normals to this coin. And if we did, it would probably be in the form of a normal map and not something procedural, which gets me to one very important thing, and that is the way you're going to set up most of your materials, or at least a lot of your materials, is by using texture samples. So this allows me to put in a texture, and by default the engine comes with a few textures. So let's use the brick normal map here. We can use that to put that into the normal map here, and now we have a golden wall. Very simply by just adding a normal map. This is how much detail you can get out of normals. And if we copy over that texture sample, and instead of the normals, we'll use the base color here. And just like that, if we disable the metallicness here, we have a wall. So very often you'll export your materials, your textures, which includes a base color map and a metallic map and a specular map and a roughness map and normal map and maybe an emissive map and whatever as textures out of either Blender or maybe something like Substance Painter. If you use that, you'll get these images and those will just simply put into your material like this. And then there's a bunch of different things that you can do to influence those image textures. And of course, there's a lot of things that you can also do to make materials entirely in engine procedurally, like using a lot of noise textures and stuff like that. But for now, we simply want a shiny gold coin, so we're going to remove all of this and stick with just our gold coin, which looks pretty good at this point. One last thing that I want to show you though, now that you understand the very basics, is material instances. Because right now we just put the material that we just made onto this gold coin. But what if we want a different color as well for metal? Maybe you want to have a steel coin as well. Well, what we could do is, of course, we could make a whole new material and replicate this setup and just change up the color here to be less saturated and a little more gray, and we have something steel, which is fantastic, except for the fact that if you have a more complicated material, that's going to get very tedious if you want to change something after the fact. As well as having a lot of different materials is also something that is pretty expensive to render. So you want to limit the amount of materials that you have. And the way you can do that is by making material instances. So if we go into our content browser here, we have this as a material, and I'm going to call this a shader or a master material. And those are the ones you want to limit your use of. So you want to have as few shaders or master materials as you possibly can. The amount of material instances, on the other hand, is not that relevant comparatively. So you right click on that, you can create a material instance, and let's call this material gold. And let's create another material instance and call this material steel. And these will just function as any other material. You can just put them into where you want to have them. And let's make this block over here, for instance, have the steel material, which you can also, if you have an asset selected here, by the way, you can use this little arrow icon to put the selected assets into here. So this doesn't look like steel though, because we haven't set up the color yet. And the way we do that is going back into our master material, our shader. We can right click any of these little value nodes here. In this case, we're going to right click the color, and we can convert this to a parameter. So we'll call that color. And now if we open up our material instances, we can see that it has these parameters here. So we can enable the parameter for our color, and now we can change this color around to whatever we might want it to be. So if we open up our steel, we can change this to a more gray color. And now we're using the same material in two different instances with one parameter difference. And we'll see that now this thing looks a lot more like steel, while this one still looks like gold. And if you have been paying attention, you will have noticed that the quickel megascan materials are also material instances. So if we open that up, we see this interface, which we've seen before, because these are all material instances and these are all parameters that are made available through its parent material. And if we open that up, we get this, which is a whole complicated mess of different things, which we're not going to get into right now. These materials are very complex setups. And with that, I'm going to end off this video about materials. So we've learned a lot today. We've learned about Quixel, which is a very useful and nice tool to have in general for materials, but also for assets. We've learned about all of the technical stuff around materials and how to make material instances. So there's going to be quite a lot of information in here. Do feel free to watch this back 2 or 3 times in the future as you go along and learn more and more. I don't expect you to have all this information stick right away. As long as you have a general idea of how things work, that will be plenty enough to move on to particles next time. And the reason that you need a general idea of how things work is that while particles are a thing in and of themselves, a lot of the actual cool stuff that you're doing with your particles will also come back to the material that you're using for those particles. So we'll look into that next time. And for now, thanks for sticking with this very long explanation. Alright, let's have a little bit of fun with some particles. We have some materials on our basic level now, but to really make things feel fun and interesting and satisfying, particles is where it's at. Particles can be great for player feedback, giving things really the feeling of hitting, something like a sword attack. It can be great for atmospheric reasons. And on higher levels, you can make very interesting visual effects, like entire magic spells or whatever your fantasy can come up with. So let's go over the basics here today. Start off with talking about where we can start here, because we can make a Niagara system, but we're not actually going to start with making a system. I want to explain the difference between a Niagara system and a emitter, because it's quite simple, actually. If we make a system, just to show you, we can make a new system from selected emitters. So let's go to next. And that then gives you a list of emitters. So a system is a collection of emitters. And an emitter is something that, well, emits particles. An emitter in and of itself cannot be placed on an actor or into the world. you're going to need to, even if it's just one emitter in a system, it needs to be put into a system and then it can be spawned into the world. So let's take a look here at the directional burst, which is a classic emitter to take a look at. So if we do that, we can add that emitter to our system, and let's call this test system. And if we open that up, we'll be able to see this interface here. This is the emitter that we've added, and on the left hand side here we see a preview of what the system looks like. So this is just a burst of particles going into that direction. So let's make an emitter of our own. We can go into FX and then we can make a emitter. We can make a new emitter, copy an existing one, or create a empty emitter. Let's go here. Making a new one, it can be based. You pretty much can copy off of one of the existing emitters. So let's take our directional burst again as the base for our new emitter. And let's make a simple particle system that spawns in a couple of particles when we pick up a coin to start with. So let's call this coin pickup and prefix it with FXE, FX emitter. You can prefix it with whatever the hell you want to. And you'll see this is pretty much the same layout, except we are missing this system node. And that is because this isn't the system. This is just one emitter. And this emitter is made out of a bunch of modules that work in stages. So initially, the first thing it does is spawning the emitter itself. Here you can add a few things, but generally where we really start is in the emitter update. This is something that runs kind of like the tick event on actor for the emitter. So in this case, we start with an emitter state. We can just ignore that. And then we have this spawn burst instantaneous, which does what it sounds like. It spawns a burst of particles. So we have the spawning count here being 75 and the spawn time 0. So at 0 seconds, it spawns 75 particles. So immediately when this emitter gets activated, it'll spawn 75 particles. We can increase this to 150 and we'll see it spawns double the particles over here. If we decrease this to 1, we see it only spawns in 1 particle. And the very neat thing about this is you can see there's these little drop down menus here. And this allows you to add a little bit of more complex logic to each of these modules. So if we want to spawn count, we can say we want to have a random range integer. And there we can say a minimum of, we want to at least spawn 50, right? But we want to be able to spawn up to 200. And now every time this runs, it will spawn a random amount in between 50 and 200. And we could do something very similar with the spawn time. We could say it should spawn between 0 and 1 seconds after activation. I don't really think for this that works, so we're not going to do that. And then we have the spawn probability, which can be useful in some situations where sometimes you might want to spawn a system and other times not. You can make an entire logic system for that in your blueprint, or you can just use the spawn probability. This is the probability that when activated, this emitter will actually spawn in. So if we set that to 0.5, when we activate, half of the time, it's not going to spawn in the particles to begin with. And of course, we can set this to something like 0.1, meaning that it's only going to actually activate the particles and spawn them in 10% of the time that it gets activated. For this, we want to just spawn it always. And we can add a bunch more things to the emitter update. There's a bunch of things that we can do, and maybe after we finish this particle system, I'll jump back in and create one from scratch just for fun. But for now, let's move on to the particle spawn. So this is everything that happens when the particle first gets spawned. So we initialize the particle, meaning that we give it a lifetime, which we can set directly to just a standard time, or of course through randomness with a minimum lifetime and a maximum lifetime. We have the same thing with the color. So we can say random in a range of colors. So we can say this needs to be between blue, and I need to actually give it like some value as well, and red. And now every single particle individually will have a color that is between these two values. Since we're making a burst for when we pick up a coin, I think we want to set this to a yellow color and maybe a slightly more white-ish, but still kind of yellowish color. And that gives us this like golden sparks feel to our particles. We can set our sprite size or our mesh attributes or our ribbon attributes. These are the three types of renderers that we have, which are the very final step. We have sprite renderers, which are just 2D planes that display a sprite, which is an image. But we can also make particle systems that spawn in meshes, which is a lot more computing intensive, so you want to be careful with that. But sometimes maybe you want to spawn in a handful of meshes to go along with a particle system. For now, we can say our sprite size, minimum and maximum. And this is, again, we can set it to being uniform, which means that they're always going to be 10 units in diameter. We can set it random uniform, meaning that they're still going to be circular, but they're going to have different sizes, as you might be able to see here. Let's actually zoom out a little bit so you can see it a little bit more, which for the purposes of our coins, I actually think this works relatively well. So we're going to go back to this in a moment. And then we have non-uniform, which is they all have the same size, but they can be distorted. So they can be, for instance, longer or very shallow. And then we have random non-uniform, which I'm sure you can extrapolate what that means. There's a minimum and a maximum, and they are not uniform, so they can be stretched. I think random uniform works the best for us right here. So let's increase that range from like 3 to 15, maybe. I think that looks pretty good. Then we have add velocity. This adds just a burst of momentum to the particles the moment they get spawned, which we have a bunch of different modes in. We can do it in a cone, from a point, or just a linear direction. Linear is just one direction. If we set this to something like Z500, it'll just shoot them up, all the particles in the same direction, and that's kind of boring. We can do it from a point, which is kind of like this explosion type feeling, and that might be what we go for, but I think if we do in a cone, what we can do is we can say the direction of the cone in here, in the cone axis. So if we set this to 0 and the Z to 1, it'll burst all of the particles upwards. And then we also have the cone angle, which we can set to something like 90 degrees, which makes it disperse wider, or something like 10 degrees, which makes it disperse a lot more shallow. I think the 50, I think it was what we had before, pretty good actually for what we're trying to do here. And as always, the actual velocity that it's shooting out with is, in this case, a random range for floats. So we can say it has to be at least 400 and at most 950. Just give it a little bit more power. I think 950 might actually be a little too much. And just for a little bit of fun, this velocity speed itself already is a random range float. So we can just make that a static number. But we can do it the other way around as well. We can actually set these minimum and maximum to also be a function like that. So what we can do is we can come down here and we can say we want to have a random range float for our minimum as well. So now our minimum will be somewhere between 400 and 450. And for our maximum, we can also take a random range float and we can say that will be between 700 and 900. And that adds a bit more randomness to it in theory. Is this really practical? Not really, but it's a fun example of how you can use this modular system with these functions and functions and functions to make something a lot more complex than just putting in a single number. And this, you can really do this recursively as much as you want. At this point, we can change this to a float from curve, which in this case doesn't really do anything because for a curve, you need to have two inputs as well. Which is something we'll get to maybe when we do something like color over lifetime. That'll be fun. So for now, let's Ctrl Z through all that and just go back to a range of 400 to 750. Now, the particle update is what happens after the particle has been initially spawned, every frame of its lifetime. So here we have things like the gravity force. You might have noticed that while we're shooting these things up into the air, they're then also falling back down. And that's because we have a gravity force. If I disable that, which you can disable all these modules by just unticking their box, we don't see them falling down anymore. And in much the same way, we have a drag force, which slows down any velocity that this thing has. If we turn off the drag force, we'll see that the initial velocity that we give this thing carries over a lot more because it's not getting dragged back down. Drag is just something that's always trying to move the velocity of any given particle towards zero. And then we have our scale color, and here we get something interesting, right? So we have the RGB and alpha are done separately, and this is just the scaling of the color. So the RGB is set to 111, so that's just the color that we gave it at, I think, initialized particle. That's the color that we gave it here. And then this float from curve is using the normalized age, so that's just the lifetime of the particle on a scale from 0 to 1, to fade the alpha, which is the amount you can see through the image, from 0, which is nothing, that's entirely solid, to 1, which is entirely see-through. That way, you can see these particles fade out as they get closer to despawning. If we disable this, you'll see that they just kind of disappear at some point, rather than smoothly fading out. Now, we can do something fun here as well, which I don't think we really need to do in this case, but let's take a look at it anyway. Now, instead of just using this scale RGB, what we can do is we can look up color and find the make vector from linear color RGB. And then we can change the color into a color from curve. So now we get this gradient here, which we can use to, say, start our color off as, if we double click this, as, say, red. And that then overrides the color that we gave it at initialization. And we can say you need to move towards being blue, and then you'll see the particle spawn in as red and move towards being blue. If we move this a little bit more into that direction, you can actually see the fade from red into blue, as it also fades from this bottom gradient, which is the alpha. So this is fully visible, this is fully not visible. But again, for what we're doing here right now, that's not too relevant because we want these to just be yellow when they get spawned in. Then we have the solve forces and velocity. That's just a module that tells this emitter just do all the calculations as far as like forces, velocity, all that kind of stuff goes. And then we want to scale sprite by speed. This means that the slower the sprite is moving, the smaller they get as well. And finally, we need to add a renderer, which we only have a handful of different ones. Usually you'll be using either a mesh renderer, a sprite renderer, or a ribbon renderer. And I'll show you a couple of examples of ribbons in a moment as well. So like that, we have a thing that we can pretty much use for picking up coins. I want to do one last thing though. Here in the particle update, you can add some collision. That way you don't see a difference here, but if you put it into the world, it will actually use collision and not clip through things. And I think you can actually... I think I saw something there. Did it do something? I don't know. Now, going back into our test system here, we can remove this directional burst. And in there, we'll find, if we say in our parent emitters, the coin pickup that we just made. And here we'll see that it's the exact same thing we made, just now put into our system. The wonderful thing about this is if I make a change here, so let's say I disable the gravity here and I apply that and save it, that affects all the uses of that emitter throughout all my different systems. And I can still fine tune this specific emitter. So I can say, no, actually for this emitter, I do want it to be on. And then that will override any changes that I make to the emitter itself for that specific system. And now we can take this system and put it into the world, and we can see if we reset, it spawns in the things and they actually like bounce on the floor a little. So if we put them down just a little lower, they live a little longer, and you can see they bounce on the floor because they have collision. Now let's add that to our coin. So we can add it in Blueprint, and when we have an overlap event, we check for the third person character, then we call the coin picked up event dispatcher, just in case anything needs to happen with that. And then what we'll do is we'll spawn a system at location. You also have spawn emitter at location. That is for the old particle effect. So if you're using a cascade particle effect that you've gotten off the marketplace or something like that, you're going to want to use a spawn emitter at location. But other than that, if you're using your own things or something in Niagara in general, you're going to use the spawn system at location, which gives us our test system here. And our location will be get actor location. The rotation and scale will just be default. And then we can enable a couple of things here. So auto destroy will destroy the system when it is done playing, just to prevent it from having too much of an overhead. If you're spawning like a million systems, you don't want them hanging around for no good reason, because that's going to take up a very small, but when you scale it up, noticeable amount of your memory. So when your system finishes, you want to destroy it, unless it's something that you want to replay over and over again, in which case you can turn this off. Auto activate is what it sounds like. It just activates the moment you spawn it in. If you want to spawn something in and then activate it later, you can turn this off. But for now, we're going to auto activate on. Those last two things, very technical mumbo jumbo, you're not really going to bother with that too much. And then the output pin will be a reference to that emitter. So if you want to do anything with it in your code after spawning it, you can simply promote this to a variable, and now you have something like coin pickup system fx. I don't know what to call it. But now if I wanted to do anything with it in any other way, I have a reference to it. Now let's play from here, and when I pick up this coin, it will spawn in those particles. And of course, since we have a level blueprint set up to spawn in more coins when that coin gets picked up, I can spawn in infinite amount of coins, and well, that one is not grabbable. Never said it was a good system, but you can see how this makes picking up the coins a lot more fun and satisfying from the get-go. Now let's make one more quick emitter, just to show a couple of different things but at this point you probably understand the basic idea. So if we make a Niagara emitter here, we want to make a new emitter, which we can base off of some of the templates if we want. So we have a blowing particle system, we have a fountain, hanging particles, a static beam, a upwards mesh burst. We're going to do none of that. What we're going to do is I'm going to make an empty emitter here real quick. And for this, we will just call it dust. We're just going to have some blowing in the wind particles. Why not? So fx emitter for dust. And you'll see that this is entirely empty now. It comes with a sprite renderer, that's a default, but other than that, everything is empty. So on emitter spawn, we really don't need to do anything. On emitter update, what we want to do is we want to look for spawn. We can spawn burst instantaneous, we've already done that. We can spawn per unit, which is very useful. That spawns in a amount of particles per amount of movement of the system. But we are going to go for a spawn rate right now. And that just continuously spawns in particles as long as the system is alive. So for things like fire, if you want to have a torch, a fire, something like that, this is the kind of emitter that you use. You're constantly spawning in new particles while the old particles are dying off. And here too, of course, we can say we want to random range and float, so we want to spawn at least 10 particles per, I think this is per second, but we want to be able to spawn up to 25. They're spawning just in a static location at the moment, and they're not really doing too much. So let's go to our particle spawn and set our spawn location, which we can do through a skeletal mesh, which can be very interesting. So spawn them on a character. But we're going to do this on a shape location. That's usually the most easy way to go about doing this. So if we spawn this at a shape location, we get a couple of options in primitive shapes. So we have a sphere, which is what it sounds like. It spawns the particles on the sphere. Then we have a cylinder, which looks very similar, but you'll be able to see if I go up top. It's a little bit more boxy because it's spawning on the cylinder. We have a box, very self-explanatory. A torus, which is a donut-like shape. And then on a ring or a disc, which is, I believe, just a two-dimensional version of the torus. And then in a cone, which pretty self-explanatory. And you see these parameters here update every single time we change where we want to spawn this. So I think here we want to probably spawn them in a sphere, and the sphere will have a quite big radius. So let's do something like 500 for now. That spawns in a good amount of particles. We can change the distribution from random, which is usually what you want to have, but you can also do it direct, which makes it spawn in order around the circumference, which is kind of neat. Or uniform, which in this case doesn't really do too much. So we're going to stick with random here, which just spawns them somewhere within the sphere. Then when the particle gets spawned, we can do some velocity things. So we probably want to add some velocity, and we'll see that, oh, now that we do that, things break because this module has unmet dependencies. If you're adding velocity to your particles, you're going to need to have that solved for velocity. So we can simply just press this fix issue and it adds the modules that we need, and now velocity gets added. So let's add velocity. I think we can just do linear velocity here, and we can just say a random vector where the scale is the speed of the particle. So let's say something like 50. And now every particle that spawns in has a random direction that it gets sent in upon spawning. Maybe 150, so a little bit better. Let's stick with 100 just in between. And now that they all have velocity, that's the velocity that they get when first spawning in. So now they're just all moving into a direction from the moment they spawn until the moment they die. That's where update comes in, as we've talked about before. And where velocity is what we do when spawning in update, we actually work with forces. So instead of giving it one velocity, a force is something that is continuously applied throughout its lifetime. And one very nice force is a curl noise force, which adds a little bit of dynamic organic movement to it. And we can see the noise strength. If we put that up a little bit, we can see things spawn into one direction, but then kind of veer off into whatever other direction. And we can change the frequency here to make it a little smaller, more chaotic, or maybe a little bit more calming with something like 60, and maybe put this at like 150. And now we can see these things are kind of floating about gently. You can see it even better if I just spawn everything from a single point and put the noise strength up a little bit more. You can see things are just kind of going whichever way direction. This is a little too much though, so let's put that back to 200. Particle updates, we want to add a little bit more force. Let's add some drag. That usually makes things feel a lot more realistic, but it also requires you to update all of your previous forces. So let's add our initial velocity here and put that up to like 250 maybe. And you'll be able to see that the initial velocity actually doesn't do that much anymore. So we might as well just, maybe we can just remove that altogether and just only use the cruel noise force and increase the strength of that to something like 400 to make things move about a little bit more. And then the frequency, we can probably turn that down a little to make it a little less chaotic. Actually, I think 50 is pretty good. One thing that I also like, maybe not for this effect, but I generally do like it, is a vortex force, which is exactly what it sounds like. If we look at it from the top, it's now giving this vortex movement to all our particles. So let's set it to like 450 maybe. One thing to note though is that it is not just a rotational force, it's also a outward force, which can be very interesting because if we put this into a negative number instead, you see that it starts going the other way. And then we have an origin pull amount, which is how much things are being pulled towards the origin point. So if we set that to 500, instead of things going outward, they all go inwards. And we can, of course, make that a negative number to make things flow outward a lot more as well. Just having a little bit of this added to this particle system will probably be quite a nice addition. Now, back to initialize particle, I probably want more of them and I want smaller ones, and I also want to change their color. So there's a few more things before we end this off. First and foremost, the sprite size mode. We're going to set that to a random uniform, and that's actually a pretty good size, I think. I think I quite like that. Yeah, that feels a lot better already. Of course, if we're spawning a smaller particles, generally speaking, we want to go back to our spawn rate and increase that to something like maybe 60 to 150, just to spawn in more of these particles. And then in the particle update, we're going to set our scale color, which changes the color over the lifetime. And this time, what we're going to do is we're going to do RGB and alpha separately. So we're going to scale the alpha from a curve, just as we did before. And I think what I want to do, middle click to add a keyframe here. And I want to keep them pretty much just solid until, well, about 80-ish% away through the life, at which point they start to quickly fade out. And the same here, we can make a color there, and we can make a color from the curve. And let's spawn them in as a pinkish color, and then over the lifetime transition to blue. Is that a good curve? Something like that seems about right. That seems nice. So now if we like go into the middle of this, we can see the newly born particles are all purplish and they turn blue relatively quickly. Now, one thing I want to show off, and there's a lot of more in-depth things to talk about here. Just like with materials, particles could be an entire series in and of themselves, and I'm sure at some point in the future it will be. But in your sprite renderer, you have your material. So if we open this up, you see a few things here to create these little circles that we've been using as our particles. And you'll be able to see that that goes into the emissive color. Not the base color, the emissive color. And if we remember back to what we talked about last video, if you've seen that one, the emissive color can go beyond 1. And that makes a hell of a lot of sense. So here in our scale color, all of this is below a value of 1, which is kind of too bad, right? But if we add some dynamic parameters here, we get parameter 1, 2, 3, and 4 out of this. And we can add these parameters in our particle system. And this is a very easy way to do things. So we can multiply the output of this lerp with parameter 1 and put that into the emissive color instead. And now we have a parameter that we can change over the lifetime from something like 5 back to 1, meaning that it starts glowing very, very brightly, and then eventually will fizzle out a little bit. So here, let's say our dynamic material parameters. Parameter 1 is going to be a curve float, and we'll set our curve scale to something like 6, maybe even higher, something like 15, which will allow you to see that these things now look a lot more glowy. Just to drive the point home, if I set that to 50, they start to really very much glow. And if I set this to like 5,000, 50,000, whatever, these things become an absolute menace. But as they go on in their lifetime, they actually fade out quite nicely. So let's keep this at like maybe 150. That works quite fine. It's a little bit overkill for what we're trying to do, but I'm just trying to show off the general idea here. And now that we have that, we can say our dust effect. If we right click on that, we can just create a system off of that, and it immediately just creates a system with the same name, but with the word system after it. And we can put that into our world, and it will start spawning in all of these very bright particles, especially with our with the post-processing that we have. So maybe tone it down just a little bit to like 50. And if we increase the size of our system, you will see that it increases not necessarily the size of the particles, which that's something that we can look into at some other point. Again, if we're doing an entire series on this, I'll cover that. But it does increase the size of where the particles spawn to begin with. So if we set this to 50, it spawns them over a very large area, but every individual particle is still relatively small. Let's set it to a size of 10. And that way we have some like mystical purple and blue fireflies in our scene, which can be quite nice if we play it, especially with this intro cutscene that we have made. You can see it adds quite a little bit to it. This could look better on the outside, admittedly. And then we have the particle system that we made in the beginning, which just is there to make picking up coins a little bit more satisfying. And we could keep going forever with particles. I like particles a lot, and you should too, is the takeaway from this video. I'm going to do one last thing, and then we're going to end it there today. And that is, I'm going to add a new effects again, Niagara emitter. Let's do a new emitter and make it an empty one. We'll do an emitter update, a spawn rate here, and we'll say spawn like 50 per second. Might be a little much, let's do 10. And then on particle spawn, we give it a velocity. We fix the issues. The velocity will be like 150, let's say 250 in the Z. And then we'll also do 100 in the Y. So now it should start making a line in that direction over there. And if we add in particle update some gravity, that should start making an arc, which is way too steep. So let's make this like 500 maybe. And there's 300. And that starts making a nice and decent arc. But there's still very much separate little particles here, and that's maybe not what we want. So instead of using a sprite renderer, what we can use is a ribbon renderer. And that more or less just renders a line, a very thin line in this case, between all of the particles in your system, which can be drawn from the front to the back, which means the newest particle to the oldest, or the oldest particle to the newest. In this case, it doesn't really matter. If you have an entire material setup that uses that information somehow, this could be relevant. And if we go back to initialize particle, we can go to the ribbon attributes here, which are at the moment unset. So if we set this to direct set, we can change the ribbon width. And now we can see that the particles that we spawn in, the sprite renders themselves, we can keep them, and that's fine. But really, these are only there to give anchor points for this ribbon to know where it needs to render. And you can do some really cool stuff with this, which we're not going to get into right now, but things like creating beam effects or lightning effects, that kind of stuff. Usually you'll probably end up using ribbon renderers, at least in combination with sprite renderers, and in some cases maybe even mesh renderers. Ribbons are really powerful, and if you don't know how to use them, you're probably going to brute force it by just spawning in a lot of little sprite particles, and that's going to absolutely kill your performance. So do get familiar with these as well. For now though, thank you for putting up with all of my rambling, and hopefully it wasn't too much rambling, because this part and the last part of this course have been quite information dense, because they are such deep topics, and I do need you to be aware that they exist. Don't need you to be an expert on it. Don't even need you to understand everything that we've talked about here today. Just as long as you know that these things exist and what their use is and what their capabilities are, eventually you will get better at using them and creating things with them and learning to understand them. Level streaming is going to be one of the most important things for you to understand if you want to make a game beyond the scale of just what we've made so far. I've got a sample project here real quick to show off what level streaming can do for you, and then we'll get into the multiple ways that you can do it for yourself. So we have a level here with a streaming level inside of it, which is all nice and good. But when we start the game itself, you can see the staircase is nowhere to be seen until we move forward into that streaming volume, that box that you've seen before, at which point the level itself appears and we can do whatever we want in it. And the moment we exit that box again, the level disappears. That's the most basic setup of level streaming. We can also manually, in other ways, load and unload levels when we want to. We'll cover that a little bit towards the end of the video. So let's talk a little bit about our level streaming here. So we have this entire level setup that we have created before, and you'll be able to see on the left hand side here I have a tab called levels. If you personally don't have that, you can come up here to a window and enable levels, and that's where we can see everything we've been doing so far has been in the persistent level, meaning the level that all of the other levels, all the sub-levels, exist within. If you want to make a new level here, you can simply just click here and create new. And that gives you the option of creating a basic level, but usually when you do it through this menu, you want to create an empty level, because you're just going to be making everything in this level on top of your persistence level. And let's call this platforming 1. And in that, we can put everything that we can despawn the moment we leave this general area. So that would be something like this box brush and these cubes, potentially even like these lights we can add into that as well. Because all of this is only going to be relevant if we're actually inside of this area over here. So with all those elements selected, we can now right click on our streaming level here, platforming 1, and we can move selected actors to level. So when we do that, we see we have selected something that we are using in the level blueprint, and that will break it, at least a little bit sometimes. So we really don't want to bother with that. So we're going to not import that, and the same thing with this one, I suppose. But everything else has now been put into this streaming level. So if we toggle the visibility, we can see all those items disappear because they're inside of this streaming level. Now, for level streaming volume setups, so as we've seen at the beginning of this video, you want to right click this and you want to go to change streaming method from blueprint to be always loaded instead. You can manually say when to load and unload levels based on their name through blueprint, which again we'll talk about a little bit later in this video. But for now, we're going to go back to placing actors and we'll look for a level streaming volume. We simply place that here and we make this as big as we need to be in the details here through the brush settings. So let's see, we want to make this nice and big. And so long as we are inside of this, these level elements will exist. So that seems about right. You can make these relatively large. So by the time we get all the way over here, it will start despawning them. Actually, as a matter of fact, let's make this thing even a little bit longer and a little bit wider and add a little bit more of a level in this direction here. What we want to do is maybe we want to make a new level, and that's going to be an empty level again. And that one we will call platforming 2. And in platforming 2, let's put in a staircase or something like that. And let's put in a few cylinders here as well, just to have a little bit of platforming. We can just make one of those in modeling mode and then copy it over a few times to have something we can jump back and forth across. We are going to add in, again, another level streaming volume, which you want to have those in the persistence level. Let me check to be sure. If I select this, you can see this selected actor is in platforming 1. It's not supposed to be. It's supposed to be in persistence level. Let's make sure that we're in the persistent level and drag in the level streaming volume, and then we can make it however big we need it to be here as well, which can be, again, pretty big if we want it to be, and then also pretty high. And we probably want this to spawn in before we exit that tunnel over there, so that it's nice and seamless and we don't see anything spawning in. I'll show you in a second that it does actually actively spawn in, but that's way too big. This is a situation where you probably want to actually go into top view mode, so you can actually see what in the world we're doing, and that seems about right. So now, how do we set up these level streaming volumes in relation to the levels that they are supposed to be streaming? Well, let's real quick go back into perspective mode here, and if we go into the levels, we can select one of our streaming levels here. And with a streaming level selected, you want to come over here to the level details. If you don't have this tab yet, which is possible, you can simply press this button up here and that will summon the level details. And in the level details, we'll be able to see that we have a streaming volumes array over here, which means that we can add as many streaming volumes as we want. And this pretty much just means that as long as your character is inside of one of the streaming volumes in this array, this streaming level will be loaded. That's entirely already like programmed for you. You don't need to do anything else about it. So we can simply use the picking tool here, and we can just simply pick this streaming level for level 1, and then platforming level 2, we can add an element to that as well. And we can use the picking tool to pick the other streaming level, which is right over here. and also set this one actually to streaming method always loaded. You might think I don't want it always loaded, that's the entire thing about streaming levels, but always loaded means always loaded as long as the streaming volumes allows for it. Unless it doesn't have a streaming volume, in which case it will indeed always be loaded. So if we just plainly select the viewport now, we can see this all works just as we expect, and we have the cutscene that we've created a few videos ago now. But if I press F8 and decouple myself from my player character, you'll be able to see that everything we made over here in that separate streaming level does, in fact, not actually exist yet. Now that we're back here again, let's actually play through the game here, and you can see now everything has been loaded in over there as well. So that's the basic idea behind streaming volumes, but we can take it a little bit further than that. Now, instead of this level streaming mumbo jumbo with volumes, let's say we have a streaming level, which we can just add here. We can simply create a new streaming level again, make it an empty level, and we can call that platforming 3, very badly spelled. And for this one, let's say that we want to trigger it through Blueprint. So by default, that is the behavior it has, so it will always be unloaded unless we actively load it in through Blueprint. And how can we do that? Well, first let's actually put some things into this level, and we can do that very easily. Just a couple of decorations here, like a box and a cone and a torus. All will be added in here as part of platforming level 3. Can be just that easy, just a little bit of decoration. And add 2 trigger boxes, one to load the level and one to unload the level. I think that sounds about right. So we put a trigger box on this side to load the level, and it's very important here to keep in mind that we've been working on platforming level 3, so we want to switch back to persistent level. I constantly make this mistake, that's why I'm reiterating it, and time again, keeping it in the video here, because it is something that can cause some issues, which can be really confusing. Okay, that's one trigger box, and then we'll also put a second trigger box on this side. And then we can open up the level blueprint, which we already have open. And for this one, we'll add in a onBegin overlap. And we'll do the same thing for the other one, add begin overlap. Here we'll first check if we are overlapping with the cast to BP third person character, just to make sure that it's actually the player character that's overlapping and not something else like the level geometry or something weird like that. And then we can load streaming level. As simple as that, by name or by object reference. I'm gonna go with object reference for right now, because that's easiest. That will literally just give you a drop-down menu of all the different levels in your game. And for this right now, we want to load in platforming level 3. The wonderful thing about doing this is that it loads it asynchronously, which means that the moment this gets triggered, it will start loading while not stalling the actual game. It's going a little bit in depth here. I'll give you a brief overview of it. Maybe at some point in the future we'll go a little bit more in depth into it. But everything you do in your programming happens one thing after another. That's how computers work. They do one thing and then the next and then the next and then the next. But if you're loading in a huge chunk of your level, you don't want it to start loading all of those things in before it can move on with the next thing. Because the next thing also includes registering your player inputs, rendering the next frame of your game. And if this takes like 10 seconds to load in the next batch of a level, you don't want the game to freeze for 10 seconds while it does that. So that's why loading things asynchronously, meaning that it's done separately from the main game thread, as it's called, is very much a good thing. And now that you know this, I'm going to ruin any AAA game for you. Next time you're playing the game, pay attention when you're walking through a hallway. Because while you are walking through that hallway, in the background, the next part of the level is being loaded. That's 9 times out of 10 what hallways are used for in level design. We want to make it visible after it's done loading, otherwise it will only load in the assets into memory and not actually show them in the world. And then when we enter the other trigger box, we want to unload our streaming level. And this one we can do by name if we wanted to. And unloading also is done asynchronously. You can see that through this little clock icon. Nodes with that icon are async nodes. They work asynchronously. So instead of using a object reference like we did here, we can also in both cases use a level name. In some cases that's preferable. For now I'll just do both to show you that it works. So let's copy this name over here and paste it in there. And now when we enter one trigger box, it's going to load in those assets. And when we enter the other trigger box, it's going to unload those assets. So let's hope I remembered the sites correctly here. So now when we walk into this, it loads in those assets, and at that site, it will unload the assets. And that is how you can manually trigger loading and unloading your streaming levels. And just as a fun little aside, I'm going to take you into my own game project and show you a implementation of that and all of the cool stuff that you can do with that. Do be warned, the node setup there is very, very messy. So here in my own project, where I just put the camera speed up a little bit higher because I was moving around very slowly. All of these boxes you see here, like this one, and this one, and this one, and this one, and well, you get the point, are separate levels, and they're separate streaming levels as well. So if I go over to the levels here and I say I want to have 04 hallway, as I call it, that's this one. If I make that invisible, you can see everything about that entire box disappears. And if we go inside it, there's like a little bit of art decoration, and there's lighting, and there's some navigation meshes, and there's enemies, and all that good stuff. And I probably want to put the camera speed back down now that I'm up closer again. And that all disappears when I hide this entire streaming level. Everything here is contained in that streaming level. And while we're playing the game, and I'll just run the game real quick here. I will mute my audio though. When we first start up the game, you can see it unloads all of the streaming levels because none of them are by default loaded. Everything is loaded through Blueprints, and only the main menu, which is a couple of objects that like spawn in this UI stuff, which UI we'll get to next time. Literally, the next video I have planned is to do with building a basic UI. We can load a game. We'll also talk about save games at some point. And then it spawns in the streaming level, which you can see right here on this side. This is the level that we're in right now. That one is loaded, and that's because that was the level I was in when I saved my game. So if you take a close look at what happens over at this little side menu here while I walk around. If I walk through that door at the end of this hallway, it will unload my current level and load the corresponding level instead. So we have the combat tutorial level here. And if I go through that door again, it spawns back in the spawner tutorial, and so on and so forth. So if I go through this level here real quick, which is supposed to show you how enemy spawners work in my game and all that stuff, and I go through here, we end up in the hallway, which we were just in, which is a split hallway between going left and going right to two different objectives. So that is how all that works. I'm not going to be able to show you the entire system here because it's a little complex for this scale here, but I'll just give you a brief overview. Somewhere in here, all that stuff happens, as well as some C++ code. So what it does is when I collide with this box here that's on this door actor, it will use the level to load variable that I have on it to load that streaming level in by name. So that's one of those situations where I use it to load in by name, because what it also does, and this is kind of neat, is it looks at what your current streaming level is, the current active one. It saves that to some location, and then when this level gets loaded, it checks all of the existing doors in here and checks the level to load on this door, which is the room we just came from, and it puts the player in the right position to go forward. So if I move this door in any way, shape or form or whatever, it always will spawn me right at this arrow. This is an entire level loading system that took me quite a while to build, and I'm not going to be able to show it off properly within this video. Maybe at some point I will do a more in-depth video on it. It also includes actual loading screens, which stay up as long as the async loading is happening, which you can see. It's pretty quick, right? Because they're relatively simple levels. But this, in a nutshell, is how level streaming works in Unreal. So even if you have a game which at first glance might not look like you need level streaming because you have small self-contained levels like I have in my game. I mean, this level is laughably small for a level in a modern game. You can still make use of level streaming for a variety of reasons. Because if you don't use level streaming and you open new persistent levels every time, there's a number of downsides to that. A lot of data won't be persistent. So things like your player's HP will reset every time and you'll have to manually readjust it and save it to somewhere before loading a new level. The music will stop and restart every time you load into a new level. All those kind of things, huge downsides to opening new persistent levels every single time. That's the reason I personally went with a system where things load in and out of existence. And you should too. And after watching this video, you now exactly know more or less how to do that. For a video game, having some UI would probably be good, right? Because right now we don't really have anything. We have got this level and this nice post-processing, but we don't really have any way to communicate anything significant to our player. So that's what we're going to be looking at today, some widget blueprint UI stuff. We're going to set up a coin counter and I'm going to set up a simple HP system just to add two different things real quick. The way we're going to do that is we can make a user interface widget blueprint, which is a specific kind of blueprint that will be displayed as a UI element. So we can just use the user widget as a base and call it widget blueprints. I'll just call this HUD for heads up display. And when we open that up, we come to this Photoshop-like canvas. Well, you can put in things in here like we can put in a button and then this will function as a button. But if you want to like design a UI, the first thing you're going to put in usually will be a canvas panel. This will give you a representation of what the screen will be like. So this is a 16:9 aspect ratio screen. For now we're going to stick with 16:9 because otherwise things get weird. And in this canvas panel, we can now put other things. So if we put the button in now, we can see this button exists within this canvas and we can move it around to wherever we want. We'll probably get to buttons in a moment as well, because I do want to show you how to make and set up buttons. First and foremost, what we're going to do is we're going to add a either rich text block or just text. I'm just going to go for normal text for the time being. And we're going to set this up to display the amount of coins we have. So we can just put in coins here as the text. But then what, right? Because how do we get the amount of coins that we have into this little bit of text? That is where we can do a binding. So we can create a binding on our text and that will get us a new function here, which will have a return node in which we can output whatever we want the eventual text to be like. So what we can do is we'll get a append string node, which will let us put in two strings and combine them into one string. And then the string can be converted into a text here to be displayed. So in the top slot here, we're just going to put in the word coins with a space after it. And in the bottom slot, we're going to put in the number of coins that we have. And we've done something like this before. We need to get the player character, which will get us a character object reference, but that doesn't hold our coins. So we need to cast to our BP third person character, because there we added the coin variable. And from that we can get our coins and put that into the bottom slot. That will convert it to a string. And now we will have a UI element that says coins with the number of coins we have after it. Now we need to think about where we want to put this on the screen. If we want to put this in the top left, we can just put it here, but you can see this little weird icon here. And for all intents and purposes, really what this icon is the anchoring point on the screen. So if you have a different aspect resolution or the thing starts to scale up or down, this is what it's going to use as its anchoring point. It's always going to be scaling and changing position relative to this point. So the default positions that you can choose are top left, top middle, top right, middle left, exact center, middle right, and the same for bottom, and then also stretch out outline to just always be scaled in either the horizontal or vertical direction for top, bottom, middle, whatever, without moving in the other axis. What we're going to do, just to show you here, is I'm going to put this on the middle of the screen, and then I'm going to put the actual coins also in the middle of the screen, so the top center here. And then we have a bunch of different options here: the X and Y position, the size of the text box, the alignment, which is its pivot point. I like to usually put that at 0.5, 0.5, so it's exactly in the middle. That way, if you just put the X position to 0, you know that your text is exactly in the center of your screen. The Z order is the way widgets or parts of the widget get stacked on top of each other. So if I put in something like a progress bar here, it will be on top. But if I put the Z order to -1, it will be below. If they're both at 0 and I go into my coins and I say Z order is 1, it will again be on top of the progress bar. It's just the way things get stacked on top of each other within this widget. Then we have a bunch of options with the font and the color, and I'm not really going to bother with that. But I do want to align the text to the center here. Now, real quick, in our third-person character, I'm going to make a float for the HP our character has. And it's going to be very simple. It's going to be a system where the max HP is always 100. That's not going to be a variable or anything. And we want to display how much HP we have in a percentage. So the way we're going to do that is we will use a progress bar for that. Just put that on the bottom of the screen. This is not great UI design, I will readily admit. And here we can do the exact same thing. We're going to anchor this one to the bottom of the screen here. We'll align this at 0.5, 0.5, because again, I do think that should be the default, even though it is not. And then in the appearance, we can choose the fill color and opacity. That's by default set to blue. Of course, since it's an HP bar, we're going to set that to green instead. And in the progress, we can see if we put the percent to 1, which is 100%, it fills with green, and so on and so forth. This is supposed to be a progress bar. It also works very, very well for HP bars. We can fill from left to right, from right to left, from center fill horizontal, from center fill vertical, from top to bottom, or from bottom to top. We're going to stick with left to right because that's how most games do things like HP bars. Now, we can also make a binding for the percentage and do something similar to what we did with coins. But what I actually want to show you is we also have an event graph for our widget blueprint. And you can see our text function is accessible through here, but we also just have the normal event graph where we have pre-construct, which we're not going to use right now, construct, which is kind of like event begin play. The difference is that pre-construct runs even before construct, and this will also run when you are in engine. Like in the editor itself, if you put one widget into another widget, things in event pre-construct will still run. Event construct will only run when it actually gets added to the screen in game. And then event tick, of course, runs every frame. What we'll do is we'll get our progress bar here, and we will set the percentage, and we'll set the percentage to get our player character, which we will cast to BP third person character. And just to have this be a little bit more optimized ever so slightly, what we're going to do is we're going to do that casting in the event construct, so I only have to do it once, and turn that into a variable. And then in our get text, we can also actually get rid of this casting because we don't need to use that anymore. And that will save a little bit of performance. Not significant amounts, but hey, everything that you can save, that's always a good thing. So we can use this variable now, and we can get our HP out of that. And we can simply just divide that by 100 because 100 is our max HP. And that will give us the percentage that we want to set this to. Back in our third person character, what I will do is a event just like keyboard Z. And when I press that, I want to subtract 10 HP from my total, which is relatively easy. We get the HP, we subtract 10 from it, and then we set the new HP value. This is just for testing purposes, obviously. In the actual game, you probably wouldn't want a button to hurt yourself with. Now, we have this widget blueprint that has our coin total and our HP bar on it. But now, how do we add this to the game? Because if we just run the game, nothing actually is visible because we haven't added it yet. You can do this in a number of different ways. We're going to do that in our person blueprint itself. And I'll just make a custom event for that. I don't know if I have shown custom event yet. I think I have, right? Anyway, you can make custom events like this and you can just call those from anywhere in your blueprint after you've made them. And we'll call this add HUD to viewport. And what we'll do in that is we'll create a widget and we can choose a widget class, which includes a bunch of things that we don't care about and the widget blueprint that we just made, which will then return the object reference to that widget that this creates. So we say, hey, create an object based on this template, which is the class that we put in, and then return it as a variable. And we can use that to add that to the viewport. You can also add a owning player if you need that. And for that, you need to get your player controller. We'll get into player controller and game modes in the next couple of videos. And now if we run after this event begin play at the very end, we run the add to viewport, we will start adding that UI element as a part of our game. And now we can see our HP, we can see our coins. If I press the Z button, my HP will lower. If I go through here, we will first trigger this cutscene, which does not get rid of your UI, I should point out. But if we run into this coin now, we can see our coin counter starts counting up as well. And we can't actually get that coin because we will die. Now, if you want to be able to also remove your UI for any reason, you need to have a reference to that UI. So let's promote this to a variable real quick, so that we can keep a reference to it for later use. And when we press the Q button, we want to get rid of that UI again. So first, when we press the button, we want to actually check if this is valid, which is a nice little macro here. We can put in a object, and if that object is valid, so if it has a value, it will do whatever this pin outputs. And if it's not, it will do whatever this pin outputs. And if it is valid, meaning that it hasn't already been removed, we can simply remove from parent and then it will get removed. So we can see I can damage myself, and if I press the Q button, it will remove the UI. And there's about a million different things that we could be getting into, but for the final part of this, let's actually create a button. Something that can maybe close the game. That sounds right. A pause menu that can close the game for us. So we'll start by making a new widget blueprint and calling that widget blueprint pause menu. We'll open that up, and for this we will also use a canvas. You don't want to use a canvas for every single widget blueprint that you make, theoretically speaking, because they are a little bit more heavy on performance. You can also use a thing called an overlay. But the downside to overlays is, I will show you, they are more performance, but you can't freely move things around inside them as easily. So I don't like using them, but do as I say, not as I do. Use overlays whenever it is actually possible. I'm going to just use canvas panels for now because it's easier. Okay, what we want to do is I'm going to add an image first and foremost. And that image is going to be filling the entire screen. This is one of the rare scenarios that you would use that anchoring method. Then I will stretch that image out and I will set its color to being pretty much black, and its alpha will go down a little bit. That way, when we enable this pause screen, we will have a little bit of a darker background. And not only that, what I'll also add is I will add a blur. You can add a blurring back for the background, and if we go through the appearance here, we can see the blur strength. If I make this thing as big as it needs to be and anchor it through the entire screen, we can see it blurs the background even in this view that we have here. So just a couple of pixels, like 4 pixels, is probably enough to give us a little bit of a darker, blurry background. That just looks rather nice. Now, we want to add 2 buttons here. One for quitting the game, and we'll add that straight into the canvas panel here. So this will be our quit game button. It'll be kind of rough, I'll be honest with you. And then I will copy that over, and this will be our continue button. Do make sure that they are anchored to the center of the screen. And now we want to add some text to it. And the wonderful thing is you can actually just add a text into a button if you drag it on top of it, and it will appear inside of that button. So we'll call this quit game, and I will make the font quite a bit larger. Not that much larger, that is insane. And then we'll also add in the other one, and we'll call this one continue. Pressing F2 on the left hand side here when something is selected also allows you to change the name of that asset, just like it does anywhere else in the engine, or Windows for that matter. And we'll call this quit button, and then we'll call this continue button. Now, when we press the continue button, we want to remove this widget from the screen. And when we press the quit button, we want to just quit out of the game entirely. So we'll go over into the event graph where we have the continue button and the quit button as variables. And when we have those selected, you'll see that we have some events that we can do. On clicked, on pressed, on released, on hovered, or on unhovered. I think these are pretty self-explanatory. On clicked is when you press down on the button and also release with the cursor still on the button. On pressed is just the pressing down on the button. On release is whenever you release from the button. On hovered is when your cursor goes over the button. And on unhovered is when the cursor leaves the button. Most often we just use the on clicked for, in this case, the continue button, and we'll also add one for the quit button. The quit button is the easiest. We can simply just quit the game. That's a pre-existing node, and it just quits your game. It's as easy as that. For the continue button, we will go back to the third-person character blueprint first, implement the adding of the pause menu before we come back into this blueprint to implement the removing of it again. And you will see why in a second. So we'll add an event for enter, and when we press that, we're just going to copy over these nodes over here, which will add a widget and then add it to the viewport, except the widget class that we're going to be using will be the pause menu one. And it's as easy as that. Now, there's a few things that we also need to do here, because if we just add this to the viewport now, there's a couple of issues with that. As you'll be able to see, the game itself, we still have control over it, and we can't actually press these buttons, which is kind of an issue. So there's a few ways to go about doing what we're going to do. I'm going to show you what makes most sense to me. First and foremost, we need to get the player controller and set the inputs to the UI only. That means that it's not going to impact the game anymore. That will also immediately give us a widget to focus on. So that's going to be the widget that you can interact with. So we can just take the pause menu widget out of here. And now when we press the enter button, we will see we no longer have power over our gameplay when I move my cursor around, and I can highlight the button. But you can't actually see the cursor, which is kind of a problem. So what we can do as well is in the player controller, we can show mouse cursor and set that simply to being true. And now our mouse cursor will actually show up in game when we do this as well. And that is what we want at the end of the day. So you can do that all here in your enter press if you wanted to. What you can also do is take this out and just put that in for your event construct. So when this thing is constructed, it will set the input mode to UI only and set the mouse cursor to show, and we'll just get the player controller. And for the widget that needs to be focused, you can just get a reference to self, because that is a widget in this case, so that will work just fine. Do be aware though that since this is a single player game that works, if you have a multiplayer game, you're going to need to specify which player controller you want to use. But this is a series for the basics, so we're not going to bother with multiplayer and networking stuff because that complicates things needlessly. Either way, you'll be able to see that the functionality works the exact same way. So if we press the quit game button now, it will quit the game because we already have that hooked up. Now, for continue, we want to do a couple more things. And that is we want to remove from parent ourselves, this widget itself. But we also want to show mouse cursor to be set back to false because we don't want the mouse cursor on screen the entire time. And we want to set our input mode to game only. So we actually get control back over our game, which is kind of nice. And you'll probably want to flush the input so that your left click that you need to do on the button doesn't get registered as a gameplay input. And now we can press enter, and when we press continue, we continue the game. One last thing though is you can see the particles and everything is still moving in the background. So the game itself isn't strictly speaking paused, we just don't have control over our character anymore. But that's easily fixed by just using the set game paused. Here we set it to true, then we copy it, and we set it to false when we continue the game. And now you will be able to see that everything in the background also stops moving when I pause, which for now doesn't really matter, but if we had something like an enemy AI that's chasing us when we pause the game, we want to also pause that thing chasing us, right? You don't want to pause the game and then die. That would be really bad. So that's the basics of how widget blueprints work and how you can set up an AI with simple programming in your widget blueprint itself as well. Hopefully it was helpful. Next time we're going to dive in a little deeper into either player controllers or game modes. We're going to cover both of them, but they'll probably be separate videos because that is very important. We've been using this player controller thing in this episode, but what actually is that and how can we use it and what is it even useful for? We'll talk about that next time. It's time to get a little bit more technical about some things, and we're going to be talking about player controllers today, because so far everything that we have done has been inside of our third-person character blueprint itself, and while that works perfectly fine, that also limits us to only being able to use this blueprint. What if we want the player to maybe change into using a different kind of character or something like that? That is where player controllers come in, because everything we're doing we can also do through a player controller. The default engine setup uses the blueprint for the player character itself to put all of its programming in, and honestly I personally also prefer doing it that way. You could very well also put all of your input controls in your player character and do it through that way if that makes more sense to you. We're going to do all of this business that we added last time with the UI, adding it and removing it through the player controller instead, because we need to pass in a player controller anyway, and this way what we're doing is we're always getting player controller 0 instead of the player controller of the player that's actually doing this action, if that makes any sense. So let's get into that. Just like most other things, we start by making a blueprint class, and we can make a player controller as one of the common ones. And usually I prefix that with PC for player controller, and we'll just call that player controller, which is very bad naming, but it'll work for now. And this is just another blueprint, just as you're used to. You will note that this doesn't come with an event begin overlap like other ones, and that is because this is not really something that you place in the world and interact with in that way. It technically does exist in the world, but that's more of a technicality than it actually being useful. So let's copy over what we put in here, and with copy over I mean just cut it out here and paste it into here. And now the wonderful thing is we don't actually need to provide the get player controller here, because we are inside of a player controller. What we can simply do is we can get a reference to self, and that will be able to plug into anything that needs a player controller. Now we do need to actually make a variable here for the UI, because we didn't copy that over, but we very much can just copy that over as well. And just like that, we have moved that code into our player controller. So now we'll see if we run the game, we don't have the UI anymore because we don't trigger it from the third-person character blueprint anymore. And the way we're going to fix that is through making a game mode, because we need to set the default player controller through the game mode. So let's make one of those as well. Make a blueprint class which will make a game mode form, and I like to prefix this with GM for game mode, and we'll call this tutorial game mode. And opening that up, we will see on the right hand side here in the details panel, we have a bunch of different default classes that we can use. The game session class, the game state, the player controller, the player state, the HUD class, the default pawn, the spectator, and so on and so forth. So the default pawn is what will spawn in at your player start. So for that, of course, we want to spawn in the third person character. And then the player controller is the player controller class that we will be using to control that character. So by default, that's just set to the base player controller. But we've made our own player controller here, so we can enable that as the default. And all those other ones we might get into at some point, they're not very relevant for right now. Now, going into our project settings, we can look for game mode, and we'll change our default game mode to our GM tutorial game mode. That means that any level we make, unless we specify otherwise, is going to use that game mode to drive all of those decisions. You can go into the world settings here and you have a game mode override, which by default is set to none. And if we wanted to have another game mode for this specific level, we could override that game mode. But now, assuming that this is actually hooked up into event begin play, which I kind of maybe forgot, doing all that, we have our UI back, which we can add again, and then we can continue, and everything works as it did last time. So in general, when something needs a player controller input, it is easier to just put it into the player controller, because that way you can just get a reference to self and put it in there. And beyond that, you can really put anything that you would put in your player character itself also in the player controller if you really wanted to. Now, what kind of code would you place in your game mode is the next logical question you might ask. And these are kind of like the rules. It's called a game mode because you can change these about. If you have a deathmatch game mode in your shooter game, or maybe you have a capture the flag game mode, all these kind of rules that these different game modes are reliant on, you would program into your game mode class. So in this case, we have a system where we have like these coins that we can pick up, right? And that code exists entirely on our character at this point. Let's see where we have that. Actually, it seems like that code exists on the coin itself, which also works perfectly fine. But maybe, instead of directly saying this coin is just going to add things to the player character, what we could do is we could cut this out of our coin code, and we could put that into a custom event in our game mode, and we'll call that custom event collide with coin. We'll add a parameter to that, and we'll call that object, something simple like that, and we'll make that a actor object reference pin, which we can connect up to this. So if whatever is calling this has collided with a third-person character, then that third-person character gets his coins increased. And the wonderful thing about this is you might be asking, why would we ever split up our code like this? This seems very, very counterintuitive. Well, the wonderful thing is, and now we're going to get into a little bit more of a technical explanation on the coding parts, is right now this is a custom event, right, which we can call. That's entirely fine. But what if we actually threw away this custom event and instead we made a new function called collide with coin? Name is already in use because I didn't compile previously. Now that we have this stored in a function, and we can put this in as a parameter there as well. Now this function will do the exact same thing, but remember way in the beginning of this entire course when I described actor hierarchy, the actor having a child, that being the pawn, and the pawn having a child, that being the character, and the character having a child, that being our BP third person character, right? Well, a child can actually take a function that exists on its parent and say, well, it's kind of nice that you think that that needs to function that way, but actually when it's related to my specific kind, so an actor might say, if I collide with a wall, I need to stop, right? But maybe you have a child of the actor, that would be a ghost. And you can override that function on the actor that says, I need to stop moving when I hit a wall, on the ghost. So when the ghost sees, hey, I'm colliding with a wall, it will do something else. And I'll just show you a practical example of that to make it a little less confusing. So what we can do is we can get the game mode tutorial game mode here, and we can create a child blueprint class of that. We'll just call that GM tutorial game mode child. And we have a lot of overridable functions here. Most of those are provided by the engine, but that will also now include collide with coin. So if we make that, it will first run whatever the parent function is, but we can remove that and put our own new functionality in. So if we make a base game mode that has a potentially just empty collide with coin function, then we can make 5 different game modes and implement whatever we want to happen when a player collides with a coin for all of those separate different game modes. Instead of having to program 5 different types of coins, all we need to do here is we need to get a reference to our game mode, which we can simply do by get game mode. We can cast that to our GM game mode, which will also work when the game mode is a child of this one. So if we have 5 different game mode children that all stem from this game mode, this cast will just straight up work. Collided with a coin, which is the other actor. And now whatever we do in our other game mode will get triggered through the game mode instead of through this coin, which is a lot more flexible. Now, if you have a game which only has one game mode, this probably doesn't matter that much, right? If you're just simply making a platformer that only ever has that one game mode and is not going to have any other need for any other code to run when something like this happens, this might be overly complicated. But it is a good thing to understand how a system like this works, because this is how a lot of games in the end actually end up functioning. Is these objects might not directly do anything. They just call to the rule set, which is the game mode, which then actually executes the code that needs to be executed. That way it's a lot more manageable and a lot more modular to create new code and change existing code. So that is the player controllers and the game modes, mostly the game modes. I personally don't really care for player controllers for the most part, I'm going to be real with you. It's nice to be able to add some things in here in a much simpler way, especially with multiplayer focused things. But mostly the important thing to take away from this video is the way you work with game modes. All that said, next time I'm going to do something else that we're probably going to actually put in the game mode, and that will be saving and loading save games. That can be a relatively complex thing, so tune in next time to see how we make that all work. Let's make some save games. If you're making a game, you want your player to be able to play, save their progress, quit the game, restart the game some hours or days later, and then pick up where they left off. Today we're going to go over the very basics of how you would set that up. And let's just immediately jump into it. First things first, we're going to make a new blueprint class, and this one is actually not going to be in the common ones. We're going to open all classes and look for save game. This is a object that you will be able to save to a file on the hard drive or SSD or whatever of your player, and then read from at a later date again. Let's call that blueprint save game. And simply put, this is where we will store all of the information that we're going to be saving. You can also put in some code in here. I've honestly never personally used that before, So what we are going to be saving is going to be a few variables here, and that will be our coins, which will be a integer, and then we will also save our health, which will be a float. And let's also save the player's location, which will be a vector. Now, there's a bunch of other things that you want to probably be able to save, and this can get very complex and very busy very quickly, because you're also going to probably want to save the coins that have been picked up. So that way, when you reload the map, you can destroy all the coins that have already been picked up, so you can't pick up some coins, save your game, quit, reload the game, and pick up those same coins again, and same with enemies, and so on and so forth. That can get very complex very, very quickly. Today we're going to stick to these three little things, but the basic idea remains the same. You're going to set the values of these variables, you're going to save that to a file on disk, then you're going to read these variables again and put them back into the appropriate actors. The way we're going to do that is going to be through the game mode here. So I'm going to set up a custom event for save game in the game mode, and we'll start off by creating a save game object. There we have to choose a class, which will be our BP save game, that will return a object of the specific type BP save game, which has access to these three variables that we have made. After we've created that, we can set the coins, and we can also then set the health, and we can set the location. Just like we would in any other variable type, we can just set these values to whatever we want them to be. Of course, in this case, we want all this information to come out of the player, so we'll get the player character, and we will cast that to BP third person character. That way we have a reference to our player. From there, we can get our coins value, we can get our, I think it is called HP, very bad naming conventions on my part, and we can get actor location. Hook that all up into the proper variable setting nodes. So now when we save the game, we're creating a save object and putting all of the values properly into the variables that we've created for them. After that, we can save game to slot. So we get the save game object that we made in this first node over here. We can plug that into the save game object, and then the slot name, we can give it any name we want. If you want to have multiple save slots, this is how that would work. You can have an array of slots, for instance, which is theoretically endless, and you can save them to specific slot names. You could even let your player just put in the slot name themselves. So long as the slot names don't match each other, they will just be saved as separate files. For now, we're just going to hardcode in the fact that we're going to just call the save slot save to keep things simple, but know that that is a possibility that we might make a separate video on in the future. And saving your information really is as easy as that. If you run this custom event now, it will write something to disk with this information in it. Now, saving the game is kind of a useless thing to be able to do if you can't then load that data back into the game. And that's where we get into the interesting part. So let's make another custom event and call it load game. Now, when we load the game, the first thing we want to do is we want to check whether or not the slot with the proper name here even exists to begin with. So there's a node for that. Does save game exist? And we can put in a slot name here, which will be save. And that will give us a bool value, which tells us, does this save that we're trying to load even exist in the first place? Because if it doesn't, of course, we're not going to be able to load anything out of it. But if it does, we can load a game from slot. And again, we need to put in our slot name. And then we get a save game object reference. This is a generic save game. If we want to try to get our coins out of this, that's not gonna work. So we first need to cast that to our BP save game here. And now we can get our coins, we can get our health, get our location, and set all those values into our third-person character. So I'm just going to copy over what we put in here, which is get player character, cast to third-person character. And from there we can set the coins, we can set the HP, and we can set the actor location. And then, just as we did before, we're going to hook everything up into their corresponding setting node. And now, if we try to save the game, it will save it all to a file with the slot named save. And when we try to load the game, as long as the save game with the name save exists, it will load and then set all that information to the right character. So let's make a couple of buttons on our player character to actually trigger the save game and load game events. So opening up our third person character here, I'll add a S for saving and then an event L for loading. In both cases we're going to get the game mode, which I can just put in the middle here. I only need that node once, and we'll cast to our game mode tutorial game mode, which we'll also do in both cases here. And then from there we can save game and we can load the game. So let's see if that works. Right now I'm standing here. If I walk over here and I press the L key, nothing happens. But if I press the S key, we don't really get any confirmation. And the S key is a really bad key because that's also in WASD. So I'm going to change that in a moment. But if I walk over here and I press the L key, I'll get teleported over to the place where I saved. If I now damage myself a little bit and I press the L key again, you'll see my HP also restores. And if I restart the game again, I will be back to just the default place and health. And if I load my game, you can see I change place and my health goes back down. Let's just run this cutscene for a moment. I can pick up a coin and load my game, and you can see I have not picked up the coin again. But it doesn't actually like reset the level or anything. So the trigger box that has been removed after triggering that cutscene, you can see still is nowhere to be found, because the only thing I did is execute a little bit of code to teleport me and to reset my stats. There's nothing about the level itself that actually gets reloaded, and that is the case in most like checkpoint and save systems in a lot of games. It doesn't actually need to reload the entire level because that would be very inefficient. Anyway, let's try and pick up a few more coins here, and then I will save. I will walk away, I'll damage myself a little bit and load again, and you can see this time I remain at 2 coins, I'll get my HP back, and so on and so forth. So we have a functioning, albeit very limited saving system. Now combining this with what we did before, and maybe instead of triggering this through just pressing the S and the L key, we add something to a menu, a save button to a menu, which calls that function on the game mode instead. It will work the exact same way. So if you want to implement this into a UI, which you probably do, you should be able to easily do that with this video and the video about widget blueprints that has gone before. So now you can save and load game data, and of course there's just 3 pieces of data in an actual save file. You're going to add in so much more separate data. It's not a very complex thing, it's just a very tedious thing to put all of that in there and get that all back into the places where it belongs when you load that data. Now that we have a functioning game, more or less anyway, you're going to want to package this game and putting it on itch.io or Steam or whatever platform you might be publishing on. Let's go over some of the things you want to do before looking into that. First and foremost, we're going to come up here into our project settings, and there we're going to look for the default map. We have the default map on Editor Startup. That is the default map that will open up when you start up your project. But you also have the default game map, which can be something different. We're going to set this to being our level 2 for now. And we might as well set level 2 to be the Editor Startup map as well. You could also make a specific like loading screen map, by the way. and if you put that in this transition map, whenever you load into a new level, it will load you into this map while it's loading the other level, which can be quite nice. We're not going to do that for now, but do know that that exists. Then, if you have multiple different levels, like a lot of levels, a full game, and you build your game, which we'll get to in a moment, you might notice something odd. And that is when you try to load a couple of those levels, it's not going to work. Because for some reason, and this is really annoying, Unreal doesn't always build all of your levels right into your build. It's kind of weird. So we have a separate setting for that as well. In our project packaging, we have this list of maps to include in packaged build. And here we can add specific assets that we want to include in our packaged build. We don't need to add in every single asset in the game that we're going to add, but for some reason, levels can be a little iffy sometimes, and you might want to add certain levels. So you can choose a file from computer. It will open up your content folder from this project, and you can add in whatever assets you want. For us, that would, for instance, be the level 1 UMap and the level 2 UMap. This should automatically also include all of these streaming levels in the persistent levels that you're including. So you don't need to go through and add all of these streaming levels as well, at the very least. Now that all that is set up, what we'll do is we can come up here to platforms. And I don't have a SDK for Android or HoloLens or iOS or Linux or all of this, but one for Windows I do have. And I do believe the Windows one, assuming you're working on a Windows computer, should be included by default. If not, there's this page on the Unreal documentation that walks you through it. It should be installed through whenever you install your Visual Studio, including the Unreal Engine and the Windows 10 SDK. So you might have to do a little bit of research if you don't have that. If you want to package for any of these other platforms, of course you're going to need to go through and find the SDK that you need for those. That's not what we're talking about here today. We're just going to be focusing on Windows. From there you can build something as a debug game, as a development build, or as a shipping build. For the most part, the difference here is things like when we used the print string nodes, we probably have one in here somewhere. If not, we can say print string. This one has a warning on it, development only. And that means if we package this thing as a shipping game, it's not going to include those nodes. So all your print strings that you're using for debugging and weird stuff like that, it's not going to be in the shipped version of your game. So you don't need to go through your entire blueprint code and delete all of those little nodes, with a good chance that you forget one or two and those end up in your game. So that's when you use shipping mode. Development and debug are, well, pretty much what you imagine it to be. This is a development build that still includes all of that stuff, and a debug build I've personally never actually used, but I imagine it has some more debugging tools. So by default, your project settings will be set to development, so we're going to change this to shipping. You can also change this somewhere in your project settings if you always want to build a shipping build, but by and large, you're going to build your development build 99% of the time, and then you're going to build your shipping build once. And then whenever you need to patch an update into your game or whatever on Steam or Itch or whatever, then you do a shipping build again. But it's so rare that you do a shipping build, comparatively speaking, that there's no real reason to take your project settings off of development to begin with. And then we're going to go up here to our build settings, and we want to change our lighting quality from preview to production, because we're making a production quality game now. And then we're going to, just to get everything properly build, like our lighting, if we have any baked lighting in Lumen, you probably don't, so that'll be fine. But things like navigation meshes, some other stuff, we're going to click this build all levels button, and that might take a little while to complete. You can just come back up here. You can cook the content, which is just preparing everything to put them into place so that they can be packaged. If your content isn't cooked yet, you will automatically do that when you package your project. So then you just simply package project. You choose a place to package it in. So there we can go make a folder called builds or something in our project folder. We select the folder, and you can see this output log starts generating a bunch of output stuff while it is building our game and making it into an executable that we can then again upload to whatever platform that we're working with. The first time packaging your game might take a little while. Then after that, anytime you package the game again, specifically if it is to the same file location as well, it will be much faster because it's only recooking all of the new changes. And if you have a fast CPU, like in my case, it also goes pretty quickly. And it's a pretty small project. So now we have this folder here, which holds a Windows folder. And in that we have our executable file. And if we open that up, we will see we have the game that we made as a standalone executable. And everything will work perfectly. I did not put back the trigger boxes there, but you can see the code that we made, for instance, for the coins will work perfectly fine, and it's just the game that we have made over these past however many parts that this series has been. I think this is part 18. And with that, we are finally at the end of all this. So if you are interested in learning more, I've got a bunch of other tutorials about like individual features and making individual things, but I've also got an entire course which, as of uploading this, I think is mostly done as well, about taking the next step and going from working in purely only Blueprint to taking a step into learning about C++ coding for Unreal Engine as well. So that is, I am dead. So that is also worth taking a look at. For now, we're going to leave it there for today, and I wish you all the best of luck with whatever games you are working on making. I also don't have an exit menu, so I need to order 4 out of this. Do remember to make a quit game menu. That is very important. And a very big thank you to all of my Patreons. You can see them on screen right now. If you want to help out supporting the channel, there's a link down below in the description to the Patreon page. And a special thanks to my Cave Digger tier Patreons, Sir J. Thomas,